Real-time data processing is one of the hottest things in data engineering right now. In this course, we're going to be covering Apache Flink, we're going to be covering Apache Kafka, we're going to be covering how to use these things to process data in real time. You're going to be able to connect to an actual Apache Kafka cluster in the cloud that is attached to the Data Expert Academy. You'll be able to process clickstream data in the labs, and you'll be learning a lot about the complex windowing functions that are available in Flink, such as count windows, sliding windows, and session windows. That should be a really fun time as well. And I really hope you enjoy this many-hour course. If you want to learn more about how to do this in the cloud, check out the Data Expert Academy in the link in the description below. I can get you 20% off.
Well, what is a streaming pipeline? This is a great question. There's a lot of words that we're going to talk about today. There's streaming, there's real time, there's near real time, and then there's micro batch. We're going to talk about each one of those and get very clear on the definition of these words, because as a data engineer, you need to understand the differences between these, whereas your stakeholders are not. Your stakeholders are not going to know the difference. Like if your stakeholder says we need the data in real time, that might not mean use Flink. That might mean something completely different. But for the most part, what we want to say here is streaming pipelines process data in a low latency way. And in this case, what I mean by low latency is usually that means that the data is processed in the order of minutes, depending on like your windowing function or something like that. Maybe the order of a couple minutes to half an hour, something like that would be kind of your latency for like when the data is generated to when it is processed. So that's the low latency way of thinking about it. Like another word that I like to use here is intraday, because a lot of pipelines in the business world are daily pipelines. Like they actually are once a day. They kick off at UTC midnight, which is like 5 p.m. and then they run, and then they maybe run for a couple hours. They run from like 5 to 7, and then that's it, and then they're done. And so this is different, where intraday means that it's going to run more than once a day. And that's where this gets complicated. And we're going to talk about all the different ways that things can run more than once a day. So yeah, let's dig into it. Okay, we have a couple words here, right? We have streaming, we have near real time, and also micro batch, which is connected. Micro batch and near real time are pretty much exact synonyms. So like, let's go over this a little bit. So streaming, which is Flink, which is what we're going to do in the lab today, is streaming is also called continuous processing, which you can think of as, okay, every time an event is generated, we process it immediately. And so if it's processed like a river. You can think of it as like a river of literally like a stream or a river. Like the data just keeps flowing and flowing and flowing, and it never stops. That is a great way to think about it. The best example of a streaming continuous processing engine is Apache Flink, which is what we're going to be using in the lab today. Then you have near real time. Near real time is a little bit different, where instead of processing data as it is generated, you wait maybe a couple minutes or a minute or 2 minutes to collect all the data that has happened in that period of time, and then you process that data as it comes in. And the big poster child here is going to be Spark structured streaming. So Spark structured streaming is not yet a continuous processing framework, even though Databricks recently announced that they will be committing to making Spark structured streaming continuous processing framework. And at that time, when Databricks does announce that, it's going to be Flink and Spark streaming are going to be essentially the same at that point. They're going to kind of converge. Just like a lot of other technologies kind of converge, these two technologies are going to converge a little bit as well. So that's a good thing to remember. So what that means, though, is that real-time and streaming are sometimes synonyms, but they're often not synonyms. And you want to make sure that you understand the latency requirements of the pipeline and not just take your stakeholders' words. Where if your stakeholders like, oh, I need it in real time, that doesn't mean, hey, I need to go and bust out Apache Flink and get real technical. Like, I mean, it almost never means that, actually. I think in my career, when a stakeholder has said real time, when they actually meant we need a streaming pipeline, that has happened 2 times. 2 times in my 9-year data engineering career when like people have said they need real time at least 24 times. So it's like maybe 10% of the time, 10% of the time when a stakeholder says they need real time data, that means they need a streaming pipeline. And so remember that like streaming pipelines, the actual use cases for them are rare. They're like 1 in 10 of like actual pipelines, at least as a kind of a general rule that you can use when navigating relationships with stakeholders. And we're going to talk more about like what constitutes like a valid use case and what doesn't. So yeah, don't worry about that. Yeah, let's dig a little bit deeper as we kind of like learn more about the different verbiages here. So another word I said here that's not on the slide is microbatch. So you can see like near real time data is processed in small batches. So small batch, microbatch, near real time. They are like all the same. That's all the same. Like very, very like those are like exactly the same. Whereas microbatch and real time are not exactly the same. They're similar, but they're different. So it's a key thing to remember as you kind of like go through these processes. So what does real time mean from stakeholders, right? It rarely means streaming, very rarely. It usually means low latency or predictable refresh rate. So I've even had stakeholders that say we need this data in real time, and what they meant by that is they needed the data up to date, like they needed a daily pipeline up to date by 9 a.m. every day. And the data actually only needed to refresh once a day. So it's funny because as a data engineer, your stakeholder says, I need real time, but what they actually need is just a batch pipeline. They need just a regular old plain Jane batch pipeline, which hopefully is like an efficient low latency batch pipeline that is regularly refreshed and is reliable. And that's a lot of times what stakeholders kind of mistake here is they think what real time means is like reliable and predictable, and it's like different words. And that's where one of the very good things that you can talk about with stakeholders is you can have this thing called the SLA discussion, which is the service level agreement discussion, which essentially means like you ask them, okay, like when do you want the data refreshed? You can ask them that question. And a lot of times they'll be like, oh, we need it 8 hours after midnight or 10 hours after midnight or whatever. And then you can make an agreement of like, okay, our data, we can guarantee that the data will be available by then. And that conversation will be way better than like just not having that conversation and then being like, okay, we're just going to do everything in streaming and we're going to go the whole other way and just like not talk with people. That's why like data engineering is also in some ways more communication than software engineering is, because you really need to talk with people about like what their actual latency requirements are, because otherwise like you're gonna overcomplicate things. And don't do that. Don't build them a Ferrari when a bicycle will work, right? Don't do it. I promise. Like the tech debt and the pain and the maintenance that you will end up creating for yourself is not worth it. So yeah, let's talk a little bit more. There's a perspective of, should you use streaming? Is it like something that is worth it? So these questions here, I think, are going to be great things that you can ask yourself. So I'd say one of the number one things you need to ask is, do the members of my team have a streaming skill set? I want to give an anecdote here about this one specifically. So when I was working at Netflix, most of our pipelines in the security space were done in batch, right? Batch or micro batch. And there was a big push by the people in security to be like, yo, we need lower latency. Even though we were giving them like data every 15 minutes, right? We were like, that's good enough, right? We can catch the bad guy if like, well, we might catch him 15 minutes late, but like what kind of damage can he do in 15 minutes? So I don't know, from our perspective as a data engineering team, we were like, well, like, do we actually start to implement streaming and change the perspective of it? Because we have our entire team is very good at batch pipelines with Apache Spark, and we know those in and out. We are like the rock star team of batch pipelines. So, like, why would we move to something that's brand new? And we're going to have the team learn it piece by piece. And, anyways, what happened was the security team was like, we have to have it lower latency. There's no way around it. And so, one of the members of my team, he started migrating some of the pipelines from batch to streaming. And one of the things that happened was he became an island where when the streaming jobs broke, like he was pretty much the only one who could fix it. And then I kind of like started to learn about how to fix it as well. That was like where I picked up some Flink skills. But then again, it was just me and him, and we were on a team of 15. And I was always like, this is unfair. Why are we the only ones who have to troubleshoot the streaming pipelines? I don't get it. And so this is why when you're working on a team, you should understand like there should not you don't want to be in the worst case scenario where like you build a streaming pipeline and you're the only one who can troubleshoot it because you're the only one with the skill set, because that's terrible. It's a terrible, horrible, no good, very bad place to be. Hopefully not too as well, because being on call 26 weeks a year is also not fun. So hopefully you have at least two other people. So you have like 3 people on the team who understand streaming pipelines. If you, that's still going to be a little bit taxing, but not as, it should still be pretty decent. So then you also have to think about like, what is the incremental benefit? So one of the big things that can happen here is, okay, we lower the latency. Like in this Netflix example where we have 15 minutes and maybe we can lower it to like 2 minutes or 3 minutes, and it's like, okay, we can stop the bad guy in his tracks a little bit faster. We can give him only, like a couple minutes instead of like 15 minutes. That's the main benefit that we would see. And how are we going to do that? And so that could be a win, obviously. Like, and in that case, in the security space, like you can actually make a case for it. Whereas like in other cases, you can't make the case where it's like, okay, it's available, like the data is available at 3 a.m. refreshed versus like, okay, we could have had it available at 1 a.m. refreshed. And it's like, is anyone going to even be querying that data at that time anyways? Does are you going to have an analyst who's doing an emergency data analytics project at 2 a.m? Like probably not. So that's another important case to remember. Incremental benefit, like what is the actual value that we get from reducing the latency? Important. Okay. Homogeneity of your pipelines. I used this word in another presentation. Like, there's a couple words that I really like in data engineering, and obviously y'all know my favorite one, which is idempotent, and that's my favorite word. I love that word a lot. But this is another one that I really like, is homogeneity. So if you're a data engineering team and you have 99% batch pipelines, like, okay, like why add a streaming pipeline? Unless the only time that would be the case is like if you have people on the team who have the skills and there's a strong incremental benefit to it, then maybe that's the case. But generally speaking, if you're a batch team, you should stay with batch. And I also agree on the flip side, like if you are a streaming team, you should stick with streaming. And that's what Uber does, right? Uber runs with this thing called Kappa architecture, which is a streaming first architecture. So for them, like, it's almost the opposite, where they're like, okay, we have all these streaming pipelines. Why would we add a batch pipeline that's just going to complicate things? And and we're going to have more of a heterogeneous mix of pipelines instead of a homogeneous mix of pipelines. And so that can just increase the maintenance burden and the on-call overhead, like when you are considering whether or not to use streaming. And then I think this is probably one of the most important points is, okay, what is the trade-off between these 4 different options, right? So you have a daily batch, hourly batch, micro batch, and streaming. Those are going to be your 4 options of essentially how you can process this data. And a lot of times, I'm going to show on, I think, the next slide, there's a continuum here of kind of complexity versus latency and the trade-offs there, where, again, you want to go back to what is the incremental benefit, and maybe a daily batch is going to be fine. And then another important thing to consider is, okay, where are we going to put data quality? Because data quality is a lot harder to do in streaming. It's a lot harder to do in streaming than it is in batch, because in batch you have like these obvious steps, right? You have A, then B, then C, right? And then so you can essentially at any between A and B or between C and D, you can put a cut, and you can be like, okay, I'm going to insert quality here and stop the pipeline if there is a problem. But with streaming, it's like it just runs all the time, man. It just runs forever. There's not A, then B, then C. It's just always on. So data quality can be a harder thing to do, and that for streaming. So that's another kind of trade-off. It goes in the trade-off bucket, and that's where daily batch is going to have the easier kind of data quality path. So hopefully those are some things that you can consider when the next time a stakeholder asks you, hey, we need real-time data. These are things that you should consider before using Apache Flink. Okay. So, streaming only use cases. So these are some cases where there is a massive trade-off that you can't make with, like, say you use hourly batch or micro batch. There's just like, you can't use those as your options because it makes or breaks the use case. So you have to have extremely low latency for there to be any value at all. The number one example I always point to is detecting fraud. So like if someone steals my credit card, I want to have them not be able to go on a 1-day spending spree before the fraud is detected the next day. I think that that's kind of a terrible fraud detection system. I don't think that that's what they should be doing. And you should probably be able to detect fraud in a little bit more of a real-time kind of way, because that will actually make the product a lot better. So obviously there's other options here, like high frequency trading, where it's like, imagine you're like, oh man, like I found the perfect setup for a trade yesterday, right? Because the data is on daily batch, and it's like, okay, well, like good for you, bro. You can't, that setup is gone. Like you can't use it anymore. It's like too little, too late. So you have to be able to process things in a low latency way so you can actually make the trades that you're looking to make. Another good example is like sports analytics. So if you're like watching a real-time game and like, or watching a football game, and they're like doing all sorts of, have you ever seen them like draw the circles and like give the stats in the game? A lot of that needs to come from real-time pipelines, because again, if it's like, oh, that play happened, even if it's like near real time and it's micro batch, it's like, oh, here are the stats for the play that happened 5 minutes ago. And people are going to be like, what? Like, this is terrible. Boo. So, like, the key thing that I want you to remember here is there's like, for the streaming only use cases, there is an obvious signal that we should be using streaming, because if we don't use streaming, it's terrible. It breaks the product. It makes it an unusable product. Here's a good example of where things get a little bit blurry. So I would say there's essentially two areas that are kind of gray area use cases for when streaming could be used, microbatch could be used, etc., etc. So if you have master data that is upstream in your data warehouse, that is like one of the furthest upstream data sets that is then depended on by a lot of other data sets, then streaming could be very powerful, because it could make it so that all the downstream data sets can fire sooner, because the daily data will be ready sooner. And that can be a massive, massive benefit to the pipeline and when things are available. And that can cause your whole, because one of the other big things that does is it allows your warehouse to be kind of amortized, so you can use all of the compute throughout the day, as opposed to having some dead compute in the middle of the day, and then at midnight there's a big spike, which happens a lot, by the way, in a lot of different warehouses. Like midnight UTC to like 2 a.m. UTC is like a spike, and then it kind of drops down, and then as people come in to the day, and they come in around 5 p.m. UTC. 5 p.m. is when they kind of like come in, and then then you get more of those ad hoc queries, and it kind of like you get more load as like you have the data analysts and data scientists running their queries that are more ad hoc. And so if you can actually amortize your compute throughout the day, it makes better use of your cloud resources, especially like if you aren't like using like on-demand resources and you have like you're renting out your EC2 instances and you're paying the same no matter what. Then you want to maximize the compute for each one of those EC2 instances, and that can be a very powerful way to do it. And anyways, master data latency, important. So I want to talk about a use case that happened for me where I failed at implementing streaming because it was freaking really hard, dude. It was like so hard. And so I was working in notifications and I needed to work on this notifications event fact data. So this data set was essentially every row was a notification event. You can think of like a notification sent, delivered, generated. You click on it, all those different events in the event stream. But the thing is like they can be duplicated because you can click on a notification twice. So one of the things that my boss was saying, he's like, Zach, this is a perfect use case for streaming. And then I'm like, okay. And then I like pump it into streaming. And no matter what I did, it just OOM'd. Out of memory. Like even if I maxed out the memory settings, still out of memory. And the reason for that is because like the duplicate can happen at any point throughout the day. So even if I'm, it's morning and then I click on it in the morning and then I click on it at 11 o'clock at night, those duplicates still need to be managed. And so that means that you have to hold on to every notification ID for the entire day, which means that you have to hold on to everything in RAM for like the whole day, which means that, and that notification data set was like 20 terabytes. So it's like, okay, we just need good old 20 terabytes of RAM and we can just go ahead and do this, right? And obviously that wasn't in the cards. That was just like a lot of RAM. Because if you think about it from the perspective of Spark, right, one executor needs 16 gigs of RAM. That's the most that you can give it. So imagine 40 terabytes of RAM. It's just, you can't do it. So instead, like for me, in that case, I tried streaming, didn't work. And instead, I moved everything to micro batch, and that worked great. I think I shared that repo with y'all about how you can kind of do micro batch in like a tree fashion to do deduping. And it was great. And that made it so that instead of landing 9 hours, so it used to land at 9 a.m. UTC, and then after I migrated it, it landed at 1 a.m. UTC, which allowed all the downstream pipelines to pick up and run a lot sooner. And that made all the notification data sets way more up to date. And analysts loved me for it because then they didn't have to be like, oh wow, we have to wait for notifications to update, because that 9 hours after midnight meant that like some days it's gonna bleed into the afternoon of the next day. So my whole point here is microbatch can work. Streaming can work in these cases. And the last point I have on the slide is like, if you're serving data to customers, it should probably be pretty up to date because customers have a high expectation on latency. They expect your data that you're serving them to be as up to date as possible, because if you serve them like data from a week ago, they're like, what? Like, why are you doing this? So you can get some good things with that. I found that like when you're serving data to customers, one of the things that you want to be careful about is you have that trade-off, right, where it's harder to implement data quality. So a lot of times, like streaming still might not be a good fit, and microbatch still could be the better fit because microbatch is easier to implement like whole data set data quality. And even for customers, if it's an hour behind, depending on the use case, as long as it's not one of those streaming only use cases I was talking about in the last slide, they might be okay with it being an hour behind. And so that can be good. Just many days behind is when customers are going to get upset. So there are some gray areas here where streaming could be used and streaming might not be used. I've generally found most of these gray areas are going to be solved with microbatch, but I have seen some of these gray areas be implemented with streaming as well. A big one here is if the analyst is just upset that the data isn't up to date, and it's those cases where he's querying it early in the morning or something like that. Like, just let it be. Like, doesn't matter. Because what are they going to do with it anyways? Because that's the big thing to remember about, like, if an analyst is complaining that the data's not up to date, like, you need to ask yourself, okay, if it was up to date, what would change in the business? And most of the time, nothing. And so it's probably a waste of your time to reduce the latency. And so in those cases, because you think about like the velocity that business decisions are made at, most business decisions aren't made within hours. They're not like, oh man, like we're looking at this data and we need to immediately act. We need to immediately solve this problem. That never happens. Like business does not move that quickly, like ever. And so that's a big thing to remember when your analytics partners are like complaining about latency, is that like, so what, man? So what if it's data from yesterday? Like, so what? Like, it can be data from yesterday, and that's fine. It's most of the time it's fine. That's just something that you find annoying and not actually impacting the business that much, and that you get the same results anyways, even if you're making decisions based on data that's 1 day late. So you got to think about it in those cases. It's like, okay, even if the data was immediately available and they could watch it update in real time, how would that impact their decisions? I mean, in some cases, I got some news for you. There can actually potentially even be a net negative to having real time data, the most up to date data, because like then people like might be just stuck on the screen and mesmerized by the fact that the numbers keep updating, and they're like, wow, this is so cool. Like sometimes like we as humans don't need to know that. We don't need to know how the data is coming in. Like, and we can just have data once a day. Have you ever seen those people who are like addicted to the stock market when they're like looking on Robinhood or something like that, and they're watching the stock change, the value change, and they're like, wow, this is so cool. But then they get so myopic on like the minute to minute changes of the data that they waste a bunch of time, and it's like, it doesn't matter. It's just a minute to minute fluctuation. And maybe just looking at like the daily open and close of the stock market is probably going to give you, maybe even you might even make better decisions based off of that, because the minute to minute fluctuations are just noise, and it causes you to kind of overly focus on noise over signal. And so if that's happening, like you want to be careful. You want to be real careful when you're working with that kind of stuff. So key thing here, analytics partners, business moves slowly. Most of the time, if they're complaining that the data is not up to date, just tell them what would be different if it was up to date. And the answer most of the time is nothing. So, and it's beautiful. That's like one of those things that should be very relieving as a data engineer, is that like if business was moving quicker, right, and then they were like, yeah, we got to solve our problems faster and we have to have everything in real time, I think being a data engineer would be even more stressful than it already is. And so that's a good thing. So impatient analytics stakeholders can definitely be annoying, but that doesn't mean you should use Flink. Let's talk a little bit about how streaming and batch pipelines are different, because they're very, very different. They're like almost the opposite. So a streaming pipeline runs all the time. It runs every second of every day, all the time. Batch pipelines run for a small percentage of the day. They usually run, even the beefiest of pipelines will run like 4 hours, 4 out of 24, so 1/6 of the day. And that's going to be, those are those Bertha, big, giant, behemoth whale pipelines. A lot of y'all pipelines, if you aren't in big tech, they run for like 5 minutes. So like 5 minutes out of a day is like not even 1%, whereas your streaming pipeline will run all the time. So one of the things that's kind of bad about that, though, is, did y'all know that men actually pay more for insurance on their car than women do? And one of the reasons for that, one of the biggest reasons for that, is men drive cars more. And it's like, if you drive enough miles in your car, you will crash your car. Guaranteed. 100% guaranteed. If you drive, like, you're statistically guaranteed to crash your car if you drive enough. Even if you're the safest driver in the world, because you're going to get ran into, because there's just all that randomness that can happen. So my whole point there is, if you have a streaming pipeline that's running all the time, the probability that it breaks is higher than a batch pipeline that's running for 5 minutes a day. Because the rest of the time, the batch pipeline is just vibing, and it's just like sitting on the couch, just waiting to run for the next day. So in that way, like, streaming pipelines require a completely different skill set. They require, because streaming pipelines act like a web server almost. They act like a server that is like serving data and moving data and is acting like, it's very software engineering. And I think that's one of those things that is why, another reason why streaming isn't as implemented, because it's not better. It's not better in some regards as well. If you have something that's running all the time, it's not better. It's definitely not better. So that's where you can get a lot more failures, and like it's different. So you also, for streaming, it's kind of like Spark in this way, but you need unit tests and integration tests for your streaming jobs, even more than for your Spark jobs, because for two reasons. One is that it acts more like a server. It runs all the time. So you're going to need to have that software engineering mindset when working with streaming pipelines. But also, it's harder to implement data quality, like in the data quality checks, which the batch pipelines in Spark, they get that. They get the quality checks on the batch pipelines. So you get that second fail-safe with batch pipelines. So it's like, even if you're like, wow, even if I push a bad build or I push an incorrect query in Spark, at least like the data quality checks and great expectations is going to save my ass. But like, you don't get that luxury in streaming. So you need to have more unit tests and integration tests in streaming. Otherwise, you're gonna have a hard time. So remember that, like, that streaming it's a lot. Like, there's a lot of things that go on. It's a lot more complex. Oh yeah, here's that continuum I was talking about in the earlier slide. So you essentially have a continuum here from not complex to very complex, and also from high latency to low latency. So you see on the left side here, we have simple, high latency daily batch. And on the right side, we have like Flink, low latency, and high engineering complexity. So remember that, like, when you're working with latency stuff, that there's a continuum here where the lower the latency, the solution, the higher the complexity of the engineering. It's not like Flink and Spark are equal in terms of complexity, because they're not. And so, like, as you reduce the latency of your solution, the complexity goes up. So that's a good thing to remember as, like, you are thinking about, oh, should I use batch? Should I use streaming? Is send people this screenshot. Real time is actually a myth, because even with Flink, it's a myth because of the fact that there is network time. So a lot of times how it works, like, for example, for the lab today, I have this thing called an interceptor that what it does is every time my website gets a web request, it intercepts it and logs it to Kafka. And then the average latency for that step, right, is about 150 milliseconds. And then from there, Kafka has it, and then Flink needs to pick it up from there. And then Flink picking it up from Kafka, the latency there is anything from like 100 milliseconds to like a couple seconds. And then Flink then needs to also write that out to a sink. And that really depends, because Flink can use windowing. And if there's windowing involved, the latency could be multiple minutes. But if it's just like an enrichment where you're just like reading and writing rows and maybe adding columns, which is what we're doing in the first lab here, by the way, that if it's an enrichment, then we need to like the sync can be written out to almost immediately. But then there's going to be the latency on like Postgres, right? Or a latency on writing out to another Kafka queue. So what I'm trying to say here is that this step from event generation to Kafka to Flink to sync, like, I remember when I was working at Netflix and we were trying to detect security anomalies, and they have this thing called red team testing at Netflix, which is where they have people try to hack Netflix and then they inject bad data or messy data into the environments and try to hack stuff. And they essentially did a red team test, and we had all of our streaming pipelines ready to go. And for the red team test to go from like hack, compromise, to Kafka, to Flink, to sync, to alert, that process, which should be, our promise was, hey, real time. So when a compromise happens, we will immediately know about it. That wasn't the case. It wasn't the case at all. It still took a couple minutes. So it's like, I don't know, like, obviously there's going to be time in between, just because you have all the other technical steps that can happen in between when something actually happened and when something is processed and discovered and generated. So there's going to be all those different pieces, right? And so we already talked about the 4 categories here of daily batch, hourly batch, micro batch, and continuous processing. So I don't need to really talk about that as much, but like the whole idea here is real time isn't, it's not like immediate. Real time, a lot of times people think of there's a synonym of real time means instantaneous. And no, because technical things take time. And like if we could get there, I mean, I think at smaller scale you can actually get things to be close. Like you can get things to happen, and you can get alerting and all that stuff on the order of you know, a single digit seconds. But as you scale up and everything, things can take a little bit longer because it's like you have to sift through stuff, and like there's more data to look at, and like there's more resource contention, and there's like all these other things that can happen that make things a little bit slower, that make the real time part of it take a little bit longer. So there's a continuum here. That's the whole point here. And just remember, real time does not mean instantly. Let's talk about the structure. Talk about the structure of streaming pipelines. There's a couple things here that we want to talk about. So you have the sources. The poster child of streaming sources is Kafka. Kafka is been around for a long time. Like I even used Kafka like way back in the day. Like back when like Obama was president, I used Kafka back in like 2014. And so Kafka's been around for a long time. Same with Rabbit. So Kafka and Rabbit are like the two big competitors. Rabbit doesn't have as much throughput, so like it doesn't scale quite as well as Kafka does. But Rabbit has more complex routing mechanisms. So like for example, Rabbit can be like a message broker where you can do like a pub sub a lot easier with Rabbit than you can with Kafka. Whereas Kafka is more like a fire hose in one direction, and it's like more of like a big old river that like you can't really like divert. It's just like, here's my stream of events, now process them. And because of that architecture, it's really fast and can handle a lot of data. So you have the sources. You can have another source called a dimensional source. Like maybe what you're trying to do here is you have your events coming in, and you want to have that event bring in some dimensional sources. Like maybe you want to do some of that like denormalization of your fact data, where you want to bring in some different columns from like your STD table or whatever type of table you want to bring in. And these are called side inputs. So if you want to learn more about this, like I would Google Flink side inputs, and that's going to be a way to look at how you can kind of marry these two worlds. So you can have a side input of data that's coming from like a regular data at rest source, whether that be like Iceberg or Postgres or any source that's considered like a table, like a data table instead of a data queue. Where Flink and Kafka and Rabbit are like queues, and they're another word for that is like data in motion. So you can have dimensional sources that enrich your event data that can be very powerful as well. And then these things will refresh on a cadence. So like what can happen is you can set up your Flink job that will have like a dimensional data that enriches the events. And then that dimensional data will refresh on a cadence, maybe every 3 hours or 6 hours. You get to pick how frequently that dimensional data refreshes so that you get the right dimension for that event. And obviously, like if your dimensions are changing a lot, then that cadence needs to refresh very often. But you don't want to have it refresh too much, because then like you're gonna like waste all of this query and compute for data that didn't even really change. But those are the two big source inputs for your streaming pipeline, and that's where your data comes from. These are, you can think of this as like the spark of a streaming pipeline, and it's how we actually make sense of our pipelines and like what's going on with them. Your two options here are going to be mostly Flink and Spark streaming. There's other options out there as well, but these are the two state-of-the-art ones, and these are the ones that actually do like the SQL or the crunching of the data. And you can learn a lot about like how this works with these things. Flink is very powerful in like how it manages like windows and sessionization and watermarking and out of order events. There's a lot of things that Flink does well that we're going to talk about here in the next couple slides. But keeping in mind, so you have the source, then you have the compute, then you have the destination, which is where is the data going. So you process your data in real time. Like your data lands in real time in Kafka. Flink picks it up in real time, and then it dumps it somewhere. And generally speaking, there's three choices. You either dump it to another Kafka topic, or you dump it to something like the data lake. In this case, like Iceberg is probably a good example. I want to give a little aside about Iceberg real quick. So Iceberg is one of the reasons why it was created was to solve this streaming problem, where before you had Hive, the Hive metastore, and if you wanted to add data to the Hive metastore, you had to overwrite the old partition. So you had to like essentially take all of the data and overwrite it again, all the data that was already there. So there was no way to like add new data to a partition that already existed. That just didn't work. Hive didn't let you do that. And Iceberg was like, okay, we want to let people do that. I think that that's a very important thing to do, is let people append new data to partitions as opposed to having to overwrite. Because Hive Metastore was very batch oriented. It was a very big batch oriented metastore. Whereas Iceberg was like, we need to be more streaming friendly. And so that's why Netflix moved to Iceberg, is so that they could have data tables that could be populated by streaming and then easily queried by batch pipelines as well. So you get both if you use Iceberg, which is so cool. That's like of everything, that's like the number one reason to switch to Iceberg, is like you have streaming events coming in and you want to append. And then obviously you have Postgres as another sink. That can be another very powerful way to set up a sink. Let's talk about streaming challenges. This stuff is always really interesting. So one of the things, remember I was talking about how there's latency between when data is generated and when it lands in Kafka. So that is totally true. And one of the things that can happen when data is generated and when it lands in Kafka is, because there's latency, you can actually have data that was generated before other data land after it. So you have like older data that is, or you're going to have like newer data that is ahead of older data in the data set. And so the data is not in the right order, and that can cause a lot of problems. That's a big issue for streaming pipelines that you want to worry about, is how do you manage out of order events, especially like in cases of like, if you're looking at a funnel analysis, or you're looking at all sorts of different event streams that like can have out of order events, is something that I think would can be a challenge for streaming. And we're going to talk more about like what is done to kind of minimize the impact of that. And then you also have late arriving data. So late arriving data, generally speaking, in the batch world, doesn't have as big of an impact. And the main reason it doesn't have as big of an impact is because of the fact that you only have to worry about it at midnight, like maybe like 2 minutes after midnight. And like a lot of times, like the batch job doesn't even fire until 10 minutes after midnight, or even 15, 20 minutes after midnight. And it's like, okay, then you have the entire set for batch. Like you don't have to really worry about late arriving data unless it's like extremely, extremely, extremely late. And in those cases, like most of the time people are like, well, that data's gone forever and we're just going to not process it. And so you want to think about late arriving data. Flink has some interesting ways to manage that as well. And another big one is recovering from failures. So one of the things that's tricky about streaming pipelines is it's a little bit different from batch pipelines in that when it fails, you need to like reset it and then have it run again. Like, and the longer you wait to fix a streaming pipeline failure, the more and more data gets behind it, and it gets like backed up more and more and more and more. Whereas batch pipelines, that's not the case, right? You just have your one batch of data and that's it. So there's not as much pressure to necessarily recover from failures when you are in the batch world versus the streaming world. There are ways to fix this problem in some regards in the streaming environment as well, and we'll talk a little bit more about those as well. But these are the three big things that you want to be more aware of when you're working in the streaming environment, where like most of these things, like in the batch environment, like they just don't exist or they don't matter. So like these are different problems that you won't need to be aware of. So let's talk about out of order events. So Flink can deal with out of order events. So how it works is when you have an event stream in Flink, you can specify this thing called a watermark. And a watermark says, okay, all of the events after, there's no events that are newer than the watermark. And essentially, like once that watermark is hit, we can guarantee that all the events inside that watermark are going to be older than the events after the watermark. And so how the watermark works is it looks at the event time of the events coming in, and usually there's some buffer. So like maybe it's like a 15-second buffer. So like you have an event time, and then you say, okay, everything within the next 15 seconds could be out of order, but something 16 seconds away is not out of order. We're essentially guaranteeing that all of the orderedness is going to happen in the next 15 seconds. And so that's how watermarking works, is you give yourself a window for each event, and then you have like the next n number of seconds that is considered, okay, there's a possibility in this window that things could be out of order, and then Flink will fix the ordering in that window automatically for you, which is cool. That's one of the things I like about Flink. It does some really cool things for you. So that's watermarking. So we're going to cover watermarking a little bit in today's lab as well. It's one of the pieces of the puzzle here, and hopefully y'all will find that interesting. Okay, let's talk about recovering from failures. So Flink manages, there's so many different ways that you can manage recovering from failures. So the big one is going to be actually checkpoints. Checkpoints is going to be the main way. And you can tell Flink to checkpoint every n number of seconds. And it essentially saves the state of the job at that moment in time. And then it knows like where to read from and where to write to if things fail. So that when you start it back up again, it doesn't like read everything again. And that kind of leads into a segue around what are called offsets. So Kafka has this notion of what's called an offset. And essentially when Flink starts up, you have to tell it whether to do earliest offset, latest offset, or a specific moment in time. Those are the three choices that you have. Or it can pick up from a checkpoint or a save point. Those are all those things that are kind of different ways that this stuff can work out. So earliest offset means read in everything that's in Kafka. Read in all the way back, as far back as we can go. And so that's a lot of data. Latest offset means only read in new data after the job starts. So it will only read in any new incoming data. And then you have a specific timestamp, which is like, okay, only read offsets that are at this timestamp or newer. And then, okay, one of the things I want to talk about here real quick is the difference between save points and checkpoints. So checkpoints are, they're internal to Flink, and they work kind of in a way that Flink can manage things like kind of internally, and it's kind of the data that it recovers from is like this internal Flink binary, whereas save points are actually more agnostic. They are more like, you could think of it as like, okay, it's going to be more like a CSV file of like, okay, we processed this data and we got this far. Because sometimes if Flink fails, we want other systems to be aware of like, hey, this failed and this is where we got to. And so save points are more used for like other systems than for Flink, whereas checkpoints are going to be used for Flink itself. So those are kind of like the main ways that Flink recovers from failures. We're going to talk, in this case, we're going to talk more about offsets and checkpoints in the lab today. Okay, late arriving data. This is another thing that Flink can do. Which is where, okay, how late is too late? And you do have to pick the time there. There's actually a time that you have to pick around like, okay, is it freaking 5 minutes that's too late? 10 minutes that's too late? Like how far away is it that things need to be before how late is too late? And keeping in mind that there are two different, we're going to talk more about this on Thursday, but late arriving data and watermarking are related in some regards, right? Because you could think about watermarking as being like, okay, there's 15 seconds and it can be out of order. And it's like, in some regards, out of order also is kind of like late arriving because it came in the wrong time because other data was able to sneak in before it. So watermarking and late arriving data are similar concepts, but watermarking is more for like the 99% of data, and then the late arriving data is for the long tail of like the small amount of data that might come in like exceptionally late. Whereas watermarking is more for the data that arrives out of order in the window. So yeah, late arriving data is not really a problem for batch because the only time it's a problem for batch is around UTC midnight, and that's only if your jobs fire really quickly. So yeah, that's essentially it for late arriving data.
Congrats on getting to the end of the Streaming Data Pipelines lecture day 1. If you're taking this class for credit, make sure to switch over to the next tab so that you can get credit to be certified. I'm excited to see you in the lab. Hey, welcome to the Flink lab setup. So to get started here, we're going to want to clone the Data Engineer Handbook. So you can do that with either code here. You can do it with SSH, or you can download the zip. Doesn't really matter. Make sure that you have it cloned though. That's going to be the first step. And then once you have the handbook open, you'll see there's a bunch of materials here. So you want to do bootcamp materials for Apache Flink training, and then example env.env. And in here, you'll see it says a couple of things here like Kafka web traffic get from website, Kafka web traffic key get from website. So what that means is we want to go back to the Flink lab setup. This link here, bootcamp.techcreator.io/lessons/Flink lab setup. And then here you'll see there's this your Kafka credentials in this PDF. So what we want to do is we want to copy each one of these over. So we're going to copy this guy over into our web traffic secret. We're going to paste him in there. And then we're going to copy this guy over here, this web traffic key. And then we're going to paste him in here. And please make sure to not publish any of these keys in any public repo, because otherwise Confluent will get very angry at me. So then you'll see we need to get this IP2 location. So the IP2 location, you just go to this website and you'll be able to get the IP2 location API key. It's very easy, very clear thing to do there. I'm not going to do that in this call because I don't want to share my key with y'all, but make sure to do that as well. And then everything else is just set and you don't have to worry about it. So then what you want to do is you want to essentially copy this file and paste him in again and make him flinkenv.env. And we're going to say okay. And we should be able to, we want to overwrite if you have anyone there. So now we have this overwritten. Now this is our flinkenv.env. This is how we're setting up our Flink environment. So the next thing we want to do is we want to go to that spot. One second, let's go there real quick. Let's go to the Data Engineer Handbook, Bootcamp, Materials for Apache Flink Training. So that's where we're at. So let's make this a little bit bigger. So in here, right, you'll see there's a couple different ways that we can do this. So I'm going to do this all with Docker Compose and not use the make. So we have these nice little make commands that can make things a little bit easier. But what we want to do here is we want to do this Docker Compose command here. This is going to set up Docker to run. So this is going to build our Docker image. So we're doing Docker Compose mvile flinkenv build remove orphans, right? So then this the first time for me, a lot of this was already built and cached, so it was faster. For you, it might be significantly slower because you have to download all the Flink dependencies. But so what's happening right now is we are doing a pip install for all the rest of our dependencies that we need in order for our Flink container to get running. And this takes a little bit of time, so just be patient with it, and we'll be able to get through this together. I believe in us. So all this is doing is installing all the pip libraries that we need to go through. So what we're going to be doing today is we're going to be checking out this thing called start job. So start job, what it does is it looks at a Kafka topic. So the Kafka topic that we're going to be listening on is actually the one for Data Expert. So every time you do a page load for Data Expert, it puts a record into Kafka, right? So it puts a record into Kafka. And then what we want to do is, and you'll see in the Kafka topic name is Bootcamp Events Prod. And that's where it's going to be putting its values. And it should be pretty awesome. And then we have the start job where you'll see one of the things it has is this IP address. So what we want to do is this job, what it does is it actually takes the data from Kafka. Then what it does is it actually hits a freaking this API location, API, and it geocodes the IP address. So we can see where the traffic is coming from. Should be pretty cool. So we're almost done here. It's probably needs about another like maybe 10, 15 seconds here to be fully installed and ready to go. But this is really good because this is like, and if you're on Mac, you can just say make up. You don't have to have all of this freaking fancy stuff. Uh, but like the Docker Compose stuff is the one that's more universal. Okay, so you see we have our job manager and task manager started. So what we want to do is we want to go to localhost 8081, and you'll see here is our freaking Flink job manager. This is where we can see our jobs running, and there's nothing running right now. So one of the other things that we want to do here, oh, my bad. One of the other things that we want to do here is we need to make sure that our other from week one, there is a Postgres container that you need to have running. So make sure you have that running. Follow the instructions on week one to have that running. And then what you want to do is you want to go into Postgres, and then you need to run a small script first. So you'll see there's this init SQL. So you need to take this SQL and then run this SQL. Okay, this SQL just ran. You need to do this in order to get Postgres to actually be able to collect the data. So now what we want to do is we want to go back into our Flink make file. So you'll see with this, you have this make job command, and this is what's gonna kick off the Flink job command. So what we want to do is we want to paste that in and run it here, Docker Compose, and I have it running right here. You'll see like it ends up kicking off this Docker Compose command, and then it will create our Kafka stream with Flink, and then it says loading in the Postgres, and then job has been submitted with job ID. So you'll know it's running when you go into here, and you'll see processed events. You should see a nice little running thing here at localhost 8081 if you have everything set up correctly. There's one final check to make sure you have everything set up correctly, and that is going to be you want to go and say select star from processed data from processed events. And if this, make sure to put in the password there, but like you'll notice that this will have data. And if there's actual data in here, then that is a good sign that you did the right thing. So yeah, I hope you enjoy the lab. This is going to be really fun.
We're going to, obviously, you want to clone it. I sent y'all a copy of this Flink environment. So let's go look at this thing here, this Flink env. So you see this like copy example env to Flink env. So definitely do that. There's going to be a lot of these values will already be covered, and so you don't have to really worry about them. Make sure you have the week 1 and 2 database running in Postgres. Otherwise, this is not going to work. And so you want to make sure that that's running. And you don't also make sure to pull for the latest version of this repo, because this repo used to be coupled with its own Postgres image, but I don't think that that's important. I think that just having this be just Flink is the way to go. And so then what you want to do is after you have that Flink env kind of put here, right? You'll have, see here's Flink env with all of the super secret password stuff, right? Kafka password right there, all these different values here. Make sure you have your IP coding key. You got this from the IP2 location website that I linked in the Discord. Make sure you get your API key and put it here. The code will work without this, but it will be a lot cooler if you put it in. And then obviously you have the Kafka URLs. These are all the Kafka brokers for my Kafka cluster. And then obviously you have your Postgres username, password, all these things how to connect to Postgres. It's not going to work without this stuff. So you want to make sure to have that set up. And then after you have that set up, you want to go to SQL, and then there's going to be this init.sql. And you want to get this processed events table. And go ahead and we're going to copy this table over into our kind of editor here. And then we can run this, right? Obviously it's going to fail for me, or create table if not exists, right? So it will work either way, and then you'll have your processed events table. So hopefully if you do everything right here, we will see data in this table after we kind of walk through our Flink job. So before we set that stuff up and we go into Docker, I actually want to walk through the Flink code, and then we can go from there. So in the repo, you'll see there's a SRC folder, SRC job, and then there's 2 jobs. There's aggregation job and start job. So we're going to go into start job, which is going to be the one that we go with first. And what we're going to want to look at here is if you go all the way down, there's this thing called log processing. That's going to be, this is essentially like the start of the job. This is where all of our definitions and stuff are going to go from. And we can look and see how this job is actually set up. So one of the things that I noticed when I was working through this, the very first thing you want to do is you want to get this stream execution environment. So you need to give Flink the ability to say, okay, we're doing a stream environment, because Flink can also do like, you can say like enable batch mode. This actually works, right? You can actually throw that on, or I think it might be is batch mode or something like that. This is like, you can definitely, Flink actually understands that, and then it will process things a bit differently. But the default is streaming, so we don't have to worry about it. Then we have enable checkpointing. Let's change this, because this 10 here is actually in milliseconds. So let's go ahead and multiply this by 1,000 so that we do every 10 seconds, not every 10 milliseconds, because every 10 milliseconds is a lot of checkpointing. That's like too much checkpointing. And then we have, here it is in streaming mode right here. That's okay. We do set it here. So first we have our execution environment, right? Then we have our settings. So these are going to be the settings that will that we want to enable, which in this case we're just saying, okay, use streaming. Then this is what we call our table environment, which is where we can define our sources, which is going to be the table environment is what we're going to use for the rest of the time. So these higher level environments we only use at the beginning. You can kind of think of them as like the Spark context, and then later on you just work with like data frames going forward. And that's essentially what we're doing here. Is this T environment allows us to kind of work more with like what the Spark equivalent of a data frame is. And then the first thing we do is we do this create temporary function. This is very similar to registering a UDF in Spark. If you know what UDF stands for user defined function. And in this case, we're doing get location. Let's go ahead and look at that function and command click. And you'll see here what this does is get location. What it does is that you have this IP to location URL. This is from that website that we were talking about. And then what this does is it takes in an IP address, and then it uses the API key that you provided, and then it goes ahead and it tries to get the country, region, and city of the data provided. And you'll see that like if you don't give it the key, the request will fail. And if the request fails, it will just return an empty dictionary. So if you don't want to make an account, it's fine, and we'll still get data. It just won't be as cool. And so that's what this UDF does, is it takes in an IP address and it returns a JSON object of country, state, and city. That's what we're going to do with this UDF function. And you see it's called a scalar function. The reason why it's a scalar function is scalar functions take in one row or one column, and they return one row or one column. So in this case, we're taking in one column IP address, and we're returning one column this JSON object. So that's what scalar means. There's other ones like aggregating function and these other types of UDFs as well that you can work with. But in our case, we are just using scalar function. And if you're not familiar with Python, this is actually how you do inheritance in Python. So our class is get location, but it inherits the scalar function functionality. And then all we need to do is implement this. And that allows us to use all the other functions in Flink that are associated with scalar function with this without having to actually implement them ourselves. Okay, cool. That's the get location UDF. This is what we're going to use to enrich our data with or enrich our event data with location data based on IP address. So if we go back down here, let's go back to that get location call, right? So this is where we're registering get location. Great. So then what we want to do is we're going to create a couple different tables. So we're going to create a source table, and then we're going to create two sinks. We're going to create a Postgres sink and a Kafka sink. And our source table is actually a Kafka source. So you see here we say create events source Kafka. So if we go into here, this is where we actually go and define our table. And you'll see, okay, our table name is events. And this is something that is kind of, we have to call it events because that's what I called it when I set everything up. And then you'll see in here, we have our, what are we trying to say here? This is, okay, so then we have a pattern. So I need this pattern to like essentially parse the timestamp because in Kafka, the event time is actually a string, but we want to turn it into a timestamp. And this is the pattern that the timestamp needs. And then what we do is you'll see here, you see this watermark code. This is where it differ. This is like, you'll see that this like initially you're like, wow, this is SQL. And then you're like, wait a minute, this isn't SQL. What the hell is going on with this for keyword, right? This is like a really weird one. So what this is saying is the watermark, essentially, this is giving it that 15-second window I was talking about, right? And that like, so this will fix the ordering of events that are within a 15-second window. And so that is what this watermark is doing. And then this part is so nasty. This took me so long to figure out how to do. But anyways, what is going on with this? Let's talk about each step, each one of these configurations, because I don't want to just gloss over this and be like, yeah, this is how you connect to Kafka. So, you know how someone was saying at the beginning of this lecture or the beginning of this lab, are Kafka and Flink connected? They are not, and you'll see this because you see the connector here is Kafka. And say we were using Rabbit, you could also do Rabbit MQ here if you were using a Rabbit connector, or this can also be JDBC, which is the Java database connector. So you can actually have Flink also read from Postgres or from another relational database. So like Flink can pretty much read from wherever the hell you want it to read from. It's not that big of a deal. And then you have the Bootstrap servers. So these are going to be all of the servers that are running Kafka. This is usually like a cluster of servers that runs Kafka together. And then you have the topic. So you can think of a Kafka topic is very similar to like a database table. And if you look in the Flink environment, in this case, our Kafka topic is bootcamp events. Well, technically it's porcupine 78436 bootcamp events, but I couldn't get rid of the porcupine stuff because so I use Heroku Kafka. That's how I set up Kafka because I tried to set it up on AWS and do it all myself, but then I was like, wow, this is a lot of work. So I just decided to use Heroku's Kafka, which worked a lot easier. And so then we have the Kafka topic, which you can think of a Kafka topic and a database table are kind of similar. Then you have this SSL endpoint identification algorithm. This can be HTTPS and other things as well. But Heroku uses key stores. So it uses these four to do the algorithm to identify that you are someone who has authorized access. So we just have to essentially say this is nothing because there's like this weird bug if that happens. So then you have the Kafka group ID. So Kafka can have a group. So you can have you can think of this as like a schema. So you know how like a lot of times in the database world you have like prod.table name or dev.table name or you know the different it's kind of like that higher level grouping. So this can be that's what this is in Kafka, and you'll see that that's in this case this is called porcupine 78436.bootcamp. So that's going to be our Kafka group. That's what we're going to be using for that. And then we're connecting over SSL. So this is actually secure Kafka. And then these ones get kind of gnarly. This is essentially the password and the different trust certificates. If you want to look at these files, they're actually in this. You'll see there's this folder called keys, and you'll see it's like super nasty and encrypted files. Right? They're both like really crazy. This encrypted files that you could decrypt with the Kafka password, and then that gives you access to the Kafka database or to the Kafka cluster. I mean, not database. Then after that, we have a couple other things here. These are the last three, and then we have gone over all the million things that you need to connect to Kafka. So then remember how I was talking earlier about how there's latest offset and earliest offset? So what I'm going to do here is I'm just going to sneak in here, and I'm actually going to change this to, we're going to change this to latest offset. And then this can also be latest here. So what this one does, scan startup mode. So this is going to be when you first kick off your Flink job. is this going to read from the first record in Kafka or the last record in Kafka, right? And then this property's auto offset reset, this is if it fails and restarts. Do we read from the first offset or the last offset? And that's what this is going to do. Or it can also pick up from a checkpoint. So that's a separate thing. So, but checkpointing is optional. So this is required. So even if checkpointing ends up failing, then this will end up picking up where it left off. The last thing is like, okay, how is this data stored? And then in Kafka, this is stored as JSON. You can also put like CSV and TSV and other values in here as well. But the data here is stored in JSON, and that's how my interceptor dumps the data to Kafka. So that's why we have to use JSON here. So this essentially gives us a schema that we can work with and we can play around with. So then what we want to do here is we want to execute the table environment. So the table environment is saying, okay, this table exists and this is how we connect to it. So then this gives us access to this Kafka queue. Great. That's how watermarking works, and this number could be bigger or smaller. I chose 15 seconds, and it is a little bit arbitrary. You can play around with it to kind of understand like how ordering works. But yeah, watermarking is important for out-of-ordered events, though. So yeah, no problem. Thanks. That was a really great question. So so we've defined our source, which is Kafka. Now let's look at our sink here, which is we're going to have create processed events sync Postgres. In this case, right, we actually don't necessarily need this watermark here because you only really need it in one spot. But in this case, we're making another table here. So in this case, what we're doing is we have a table that has a different schema, right? You'll see it has this new geodata column, which is also varchar. But what this does is you'll see the connector here is different. In this case, we are connecting via JDBC. Our URL is our Postgres URL that's defined in that Flink environment. And then we say that our table name in this case is processed events. And then we have our username and password. And then we have the driver. So this is going to be our driver code. And this is something like when you're deploying Flink, you have to include this Java code in your deployment if you want to be able to connect to Postgres. You have to include the driver code as well. Otherwise, this doesn't work. So that is essentially how the sync works for Postgres. This allows Flink to directly access this Postgres table processed events. And keeping in mind, though, that this create table statement does not actually create a table in Postgres. This is just to have Flink be aware of the schema. So that's why you actually have to run that. You know how I said you had to create this create table at the beginning of the lab? You have to run this create table. It's because they're different, right? And so this is just to let Flink know what the schema looks like. So then you have, so that's our Postgres sync. Let's look at the last sync, and then we can talk about how each of these things actually works. So then we have the Kafka sync. So here's a Kafka sync. We have process events Kafka, and then you'll see in this case we don't use this pattern because we don't need to because it's a sync. So then we have our sync DDL, which is this is the same. You'll see this DDL and the Postgres one are the same because these are literally the same. I just wanted to show people how you can write data both to Postgres and to Kafka. And you'll see in this case, all of this is exactly the same as in the source data because it's the same cluster. You'll see the only difference here is actually the topic. You'll see the topic here is a little bit different. It's funky how it works right now. I'm doing it this way where I do this like weird split logic so that we can get that weird porcupine thing out of it that like Heroku gives me, but then I give it the new table name. Keeping in mind that and I'm sad about this because this was something I thought Heroku would let you do, but you can't change this name and create a new topic. Heroku does not let you create new topics on the fly. And then in here, you then can create your topic name and then add it to this big old thing. And then this is then our sync. And this is where we can write data out. And so we now have our sync, and we have our two syncs, and we have our source. So we have now gotten through the first 5 lines of code of this freaking Flink job. And now let's kind of like actually go to where some of this transformation logic is happening. Okay, so this gives us our Flink Postgres and source table, and you'll see that like one of the things that's really cool is this actually, you'll see this actually just returns table name. So after you create this table, you can actually refer to this table just by its table name, just like you would in a normal SQL environment. And I like Flink SQL for that reason, and that's one of the things that's really cool about Flink SQL, because Flink SQL and Flink Java are going to have like the same performance. And then in this case, what we want to do is we're saying, okay, we're going to add to the Kafka sync, insert into, and then this is what we're going to do is we're going to look at our IP address, right? And we pull the IP address this way because it's like kind of in a nested field. Because Heroku actually does this weird like IP address forwarding thing that you need to kind of extract it out. And then we want to do a date field here. So this is essentially moving this back into like a normal timestamp field because it was having a hard time Kafka was having a hard time serializing this to JSON because it was like a timestamp column, and timestamp has a harder time like serializing to string, but this serializes it back to string. And then we have the referrer, which is like, in terms of web traffic, this is like where they came from, like LinkedIn or Twitter or wherever, right? And then you have the host. In this case, this is like zachwilson.tech or exactly.com or there's like a bunch of them. And then you have the URL, which is like /signup or /login or /bootcamp or whatever. And then you have you'll see this is actually the get location call. So this is actually calling that UDF that we can then call. You see how we created the get location up here, and then we are calling it in SQL right here, and then we are reading from Kafka. That's essentially what source table here is. And then this is inserting into the Kafka sync, which is the new topic. So we're enriching it with data, and then we're moving it. So then we have the second one here. It's doing literally the same thing, where we are taking it and we are instead moving it into Postgres, and this is going to write records out to Postgres. And you want to add a .wait here on the last line of your code in Flink. Otherwise, this will just will run for every record that's in the current Kafka queue, and then it will end the job. And this makes it run continuously, this .wait. So then we have a little try catch here to in case there's a failure for Postgres. And this could also be a failure for Kafka, but like Kafka's probably not going to fail because it's like Kafka to Kafka, which is going to be like less of a bug. So then at the bottom here, obviously you have the actual like the entry point for the job where we actually call the job. So this is the job that we're going to be working with today to actually kind of go over what's going on here to show like, hey, look, we're doing stuff. So then what you want to do, now that we have that working, we can actually go into our messy Docker environment now. So what we want to do here is we want to say make down. I'm going to do make down first, which is going to, we want to kill all of the images that we have up. Then we say make up. Okay, so now our job or our environment is up and running. So let me show you that environment real quick. So if we go to localhost 8081, you'll see, okay, so this is our task manager, and you'll see we have no jobs. So this is, and here's our task manager. This is where it's running, and you'll see all sorts of different things about like Flink, the memory. You can see all sorts of crazy stuff. But the key thing here is you see there's no running jobs because I just started up the task manager, and let's kind of go over like what's going on here with our slots, right? So we have 3 available slots. So that means I can run 3 jobs at once. But if I have more than 3, then like it's going to wait for one of them to finish or something like that. But our jobs are actually designed to never finish. They're supposed to run 24/7 because they're streaming jobs. But Flink jobs can also be batch jobs. That's why they can finish. That's why some of these have finished, right? So Flink's kind of a wild one where it can do both. So then what I want to do here is say make job. So this is going to call up the Docker container again, and it's going to see how it's saying, okay, Docker compose exec. We're calling the job manager, and then we're like, okay, we're calling Flink directly, and then we're calling the start job file. And then you'll see, okay, now we have 2 jobs that have been submitted. These are the jobs to write to Kafka and the job to write to Postgres. So Flink is similar to Spark in this way, where you know how Spark, they say Spark is like lazily evaluated, and it only actually fires up a job when like there's like an insert statement or a collect statement or there's like a movement of data. Flink is very similar like that, and that's why there's two jobs that end up getting fired here, and that's because of these insert statements here. These insert statements cause two jobs to be fired, and that's what's going on. If y'all like are curious about like why there's two jobs instead of like one big job. So you'll see here now we have two jobs here that are running, and if we let's go into this processed events. So if you look at this guy, this is going to be our code here, and you'll see it's going pretty well. Back pressure 0, busy 0. Because if you remember, I changed the source to be you see how I changed the source to be latest offset. So it's only reading in new data. So like let's like load up a row. Okay, so that's gonna cause it to have at least one row of data. That let me go into here real quick. Let me delete the data here first so that we can see the new data. So okay, so I deleted the data from processed events, and let's add one more record to the queue. And then what we want to do here is if we go back here and we say select star from processed events. Okay, so you see I have one record here, and see here is US, California, city, San Francisco, right? So, and if any of y'all freaking want to like go to zackwilson.tech, you'll see that your data and location will show up here. And obviously I live in San Francisco, so this is actually pretty good and kind of creepy. I was able to do this, and so the idea here is if you see, I can go to other pages too. So if I go to like boot camp, right? Oh, let me go to exactly boot camp. It's like, because I'm like logged in over here. Okay, there we go. So now you'll see I should have generated a bunch of events there. So if I like put a limit, let's put limit 10 here. So there we go. Oh, and some of y'all were like refreshing stuff too. So you'll see, oh, look at that. Look, Bruno. I think this is Bruno. I guess this is Bruno here. Brazil. What's up? Everyone else. Do we got representation here? Oh, dude, we got a lot in here. We got some Florida. Got some Alaska. Look at that, dude. I got some freaking people in here. Here's got some Texas, right? So Sugarland, Texas. Interesting. It's a cool place. So anyways, you'll see but you see how all of this data was just available immediately, because that's what real time's all about, is it's immediately available. That's what it's all about. And you'll see this guy here actually, you can see some of these people are actually coming from different spots. Like this guy came from my Substack. So this is actually probably an event that was not from the bootcamp, because you see like there's a referrer here that is my Substack. So they came from my Substack newsletter. And you can see, oh, that's kind of like how all this is working, right? And this is the idea behind how this works. But like what you can do, right, is you'll see with the geodata. So if we like geodata and we JSON and then we say country, right, then we can like, there we go. And then we can also then count one, and we can say put group by one. There we go. Then you can see all the different countries. So we got US as leading, we got Nigeria, we got Canada, and we got Brazil, right? We got a couple of people showing up from all over the place here, right? And this is essentially what's going on, but it's in real time, right? So like as more data comes in, see there's another one. See now we have another one, VE. Is that like Venezuela? I have no idea. But like you'll see like this is a live data feed, right, of this processed events, because my Flink job is just processing new data as it comes in. And so this is pretty cool. So one of the other things this job is also doing, right, because there's two jobs here, right? So if we saw here, so you see processed events Kafka, you see it was here at this like 39.67 megabytes. And you see how like now it's a little bit higher. It got moved up to this 40 megabytes, and now it's like slowly growing. And like, so that's what's going on with this process events Kafka, because we are writing more data to this Kafka queue as it comes in, as like more and more people like, you know, spam my website and stuff like that. And so this is kind of the idea behind how Flink works, is you have kind of different values that can come into place here. So one of the things I want to show real quick though is I'm going to kill these jobs real quick. So I'm going to say, so the jobs are killed, and I'm going to say make down. I'm just going to kill the whole, I'm going to start over here. And what I want to do here is I'm going to change this to earliest, just to kind of show you the difference, right? So you'll see here, when we ran that, what there was like, see how there's like, I don't know, like 50 records? Because that's like how many people hit the website in the last like 5 minutes. But now when I run it this time with earliest offset, if we go look at the Kafka dashboard, so ours is bootcamp events. So this is going to be our actual data set that we are working with, right? So this data set is like about 15 megabytes. So I would hope, like if we use earliest offset, we're going to process all of this data again. It's going to process all the way from the beginning, and that's like what we're going to do when we redeploy this job here. So in this case, we're going to say make up. Okay, so now what we want to do is we want to then say make job. And then I'm going to show, this is going to create some interesting things in the UI that I want to also illustrate to y'all so that you can understand some other kind of pieces of this puzzle. So there we go. We have our 2 jobs running. So now let's go back into the Flink UI while we can still show what's going on here. So let's go look at this process events job. And you'll see, one of the things you'll see is like, you see how it's like red right now? And it says it's very busy. It's 64% red. And so what's going on here is it's busy because of the fact that it's, oh, there we go. Now it's really red, right? So now it's like really busy. Now it's like essentially maxed out. So what happens here is you have, you see how there's like busy and then there's back pressured. So these are 2 different kind of things that can happen because, so busy means, okay, we are at max compute. Like this Flink job cannot process any more data. And if it processes more data, it gets moved into back pressure. And essentially back pressure is the second layer, where back pressure essentially says, it tells Kafka, slow down, because we need to essentially add a little bit more latency to the data so that we don't out of memory, and so that we can process all the data that's coming in. And this can happen like, you know, if your data set goes very viral, or if your data set is like if you get a lot of hits, it's very spiked, or you get some spiky data sets, because you can't necessarily manage that yourself, because you can't just be like, oh, I'm going to stand up more Flink machines. Obviously, you can set the parallelism and have like do distributed compute with Flink as well, but you have to pick the number of machines ahead of time, and you don't know how much data is going to come in. You could have more, could have less, right? So that's essentially what's going on here, right? Is now we have our data and it's essentially running, right? You'll see now I bet it's back to, okay, so yeah, it's still processing stuff. It's still dumping everything out. So this is kind of the idea behind how this stuff works, is we have our back pressure and our busyness of our job. And you'll see the Kafka one is the same way, right? It's just maxed out, like it's just trying to struggle through it. And then eventually it will like be essentially go from like 100% to 0% because it's just going to finish everything, and it will have processed everything. But now if we look at like this query here, right? So remember, like we had like 50 rows here, right? I bet there is a lot more than 50 now, right? Oh yeah, look at that. Look at that. There's a lot more than 50 now. So now we have like, okay, see, we have our US, we have India, Great Britain, Canada, whatever IE is, Japan, right? All these different countries here. Even some that didn't even, you have null here. So that means that some of these IP addresses didn't geocode correctly, or they have like there's like a null, right? But you'll see like, I don't know, there's 44 different countries. So people in 44 different countries have visited my website in the last day. And that doesn't, I mean, it might not even be done, right? Let's, if we put like it should keep processing. There we go. So you see how it's still struggling through, right? All of the data here. And that's one of the things that is tricky about Postgres syncs. So Kafka syncs are generally a little bit more performant because of the fact that they are meant for high throughput, because you have like the queue can just be dumped in and it's fine. Whereas Postgres is not, right? Postgres is more meant for like transactional data that is like kind of not large volume, right? It has like And so you want to be aware, like when you're building out your Flink jobs, like where is the data going, and like what, dude, this is wild. This is not supposed to be so busy. Why is it so busy all the time? Like y'all need to like quit visiting my website. Like last time, that just shows you like because I did this same presentation back in May, and like it was busy for like a minute, and now we're rocking almost 4 minutes now, guys. Like so this is madness. But like this is the idea behind like how you kind of build Flink jobs. But the key thing I was trying to say here is back to the syncs, right? So Kafka is going to be a very high throughput sync that like can manage things a lot more effectively. So I imagine that the Kafka dump here is going to end up being not busy a lot sooner than the Postgres one, just because of the throughput of Kafka. And then that's kind of the idea behind how these jobs work.
Congrats on getting to the end of Streaming Data Pipelines Lab Day 1. Streaming pipelines are crazy, right? If you're taking this class for credit, make sure to switch over to the next tab so you can get credit for Day 2. I hope you enjoy it.
I wanted to talk a little bit today about what is actually going on underneath the hood of like, you saw how like on Tuesday there was we have this Kafka thing that like you hit a website and then data just shows up in Kafka, right? And so I wanted to kind of explain like more in detail of like this right here is the architecture of my entire website. So let's start over here with like stick figure man. So this is, you know, this is you or a student or anyone who's visiting my website. And then the first thing that happens is you'll see that like if I want to go to exactly.com, what happens is that request gets intercepted. So there's this HTTP interceptor. And what that does is it just looks at the request and then it logs it down to Kafka. And then then it also just passes it forward. So then exactly.com can then determine what to do with that request after it hits the server here, hits Express. But then like, okay, when that request gets logged down, it goes to Kafka, it goes to a Kafka producer, and then that Kafka producer puts it on Kafka, and then we can then read from Kafka onto Flink, and then we can either dump it to another Kafka topic, which is what one of those jobs did in day 2 or day 1, and there was the other job that dumped it to your local Postgres, right? And then it did some of that like, you know, a geocoding IP address stuff as well. So I want to talk about the other path here, right? So if it a lot of times when it hits a server, then what the website will be like, okay, is this a web page request? Which means it's like a normal, like kind of like HTML request. It's like, are you asking for the about page or the login page or the bootcamp page or like whatever page, right? If it is a web page request, then what it does is it renders it server side, because we use React, right? And it does server side rendering, and then it passes the rendered HTML to the client, and then that client is now ready for the user to work with, to click and watch videos or whatever you want to do. But if it's not, then if it's not a web page request, that means that it's an API request. And if it's an API request, that means that it's probably an update or create or delete request. So in this case, it's going to hit Postgres. Remember how I was talking about in the Q&A how we use the Pern stack here? So this is Postgres, right? Postgres over here, Express right here. We have React and Next. Next and React are kind of like coupled together. And then the whole thing kind of like runs on Node.js as well. So then Postgres will run, and this is like maybe you sign up, and then like if you sign up, that's an API request, and then it hits Postgres, and then it goes back to the server, and then it will redirect you. Because after you sign up, usually it's going to go back to another page, like the login page, or if you log in, which is also an API request, it will then take you to the bootcamp page, right? And then so this is essentially the architecture behind exactly.com. But my whole point here is streaming needs to have some type of real-time architecture like this. It has to have a way to intercept real-time events. So there's more to streaming than just Kafka, right? There has to be another layer. There has to be the event generation layer. And in this case, the event generation layer is this HTTP interceptor, and then that makes it so we can see every time an action is taken by a user, that's what happens. It gets dumped to Kafka. So this is essentially the architecture that we're kind of working with in our bootcamp. So, okay, so So what this code does is it sits between you and when you hit my server. And you'll see what it has is, you saw this, like, it's called an API event middleware. And essentially what it does is you'll see it has a rec, res, and next. So rec is the request, res is the response, and next is how, if I call next, that means it passes the request to the server. So what happens here is, first I have this line here that says, okay, should it be logged? And essentially I'm like, I don't want, like, if I'm in development and I'm doing like dev work, my website's on localhost and I don't want my development events to be logged to Kafka because I think that that's dumb because it's not real traffic. So, and then there's also, I don't want it to be a file request. So like every time that it requests like an image, like my logo or like any other sort of like the LinkedIn logo or all the different images that are on my website, I also don't want to log that because it's just like excessive. And I only care about like the web page requests and the API requests. So then we have this event, and this is the schema, right? That if you remember, like when we were working with Kafka, this is the schema that we work with. Right, and you have the URL, the referrer, you have the user agent. This could be like if it's Googlebot or Chrome or Android, right? And so then you have your schema, and then I have like this essentially if it should be logged or not. And it's like, okay, if it passes the should be logged, then it sends the message to Kafka, and then it calls next, which means that then it passes the request to the server, and then the server does what it's supposed to do. And then otherwise, it just passes it to the server anyway, like if like it shouldn't be logged. So that's essentially what this piece of code does. This is a little tiny piece of code that sits between you and my server that like essentially looks at every single request that comes in. Okay, so then we have the producer code. So this is the producer code. Or you saw how like here we have that send message to Kafka in the interceptor. Well, here is that send message to Kafka, and then I create this Kafka producer here, which has a similar sort of SSL connection like we do in Flink, where we have to connect with like all those like SSL credentials because we need to do that on the producer side as well. And then you'll see here I'm saying, okay, write to this Porcupine Bootcamp events. So this is that topic, or like I want to write this message to this table. And then I have my message object, which is essentially just the object that I have over here, this event object. I'm going to be writing that. And then what we do is we start up the producer, and then we send the data to the producer. And then this producer.send line will hopefully send the data to Kafka. If it does, then it will say, we'll get a log that says message sent successfully, and then it will say result, and then it will end. Otherwise, it will send an error message for us. But since it's just logging the Kafka, I don't want this to throw an error, because it's just logs, right? So I essentially just say, okay, it's fine. If it logs or it doesn't log, I don't care. I just want, because I don't want that to stop the traffic to my website. So anyways, those are the two pieces that happen upstream of events landing in Kafka. So now I want to talk a little bit more about the future architecture of exactly.com. And so this is, like you'll see, is very similar, except it has a couple more pieces to the puzzle here, right? So you'll see we have our Flink job down here, and then we have another Kafka topic, and then you see how we have this like listens for events, and then here's that Kafka consumer that Doug was talking about. So this Kafka consumer is just listening on this processed Kafka queue, and then what will happen is this consumer will then push events back to exactly.com, and then exactly.com will push those events through a WebSocket, and then the client will be updated in real time. So that's the idea. I mean, obviously, like we're not quite there, but this is what a real-time data product looks like. Is where you have a full loop where it has like you have data coming in, and then it goes through, and then it goes back out back to the client, and you have this like real-time event stream, and the client is very aware of what's going on. And so all this data would be updated as quickly as it possibly can. And so the latency here would be very low, like on the order of seconds for sure. And so that's kind of the idea of what the future will look like, and hopefully the future of this bootcamp, we will be able to implement more of these pieces as well to show people how to build their own real-time updating UI, so that they can have their own so they can see the real power of Flink and be able to build their own analytics dashboards and stuff like that. But that's kind of the idea of where the future is going to go with the architecture of this stuff. But for today, we're just going to be working more with, we're going to kind of be still kind of more just in this another Kafka topic and your local Postgres. So anyways, one of the big things that I think is going to be a massive, massive thing in the future and going forward, I've already seen this happen at Netflix and at Airbnb, is the whole idea of owning what's called a data product, where you have all this data that you're crunching, but then that data somehow manages to get back into that. And that's what's gonna, like, that would be the idea here with these red things that are not quite built yet, but that would be the idea, is that's how you would build a closed loop. Because you see how now there's like a loop here, right? It's like you can like, there's like you can go around in circles as many times as you want, right? And that's that whole idea of like a closed loop system is very powerful. So this is kind of the idea behind data products. I want to talk a little bit more about WebSockets, because I think WebSockets is something that not very many of you are probably aware of, like what a WebSocket even is. So generally speaking, when you are building a website, you have your client and your server, and the client always asks the server for more data, and the client almost always initiates the request. If you don't have, if the server needs to initiate the request, like say the server gets new data, and then like the client usually has to ask for that new data, even if the server got it and knows it's got it. So the way that, and that's like normal HTTP. That's how normal HTTP works. And so if you want to have more of that two-way communication where the server can send stuff to the client as well, then you have to do this thing called a WebSocket. And WebSocket is going to be how you end up getting that like two-way communication and those real-time updates. So I want to talk a little bit more about competing architectures here for like how you process data. So there's one called Lambda, one called Kappa architecture. These are the two big like competing. They're like the Pepsi and Coke, or the kind of competition, different ways of doing things. And let's go over each one. I like, just to preface this, like I've almost exclusively worked with Lambda architecture throughout my career. So Kappa architecture is mostly from reading, but I have a pretty good idea about both of them. Lambda architecture. So imagine you have a pipeline that you want to optimize, and what it does is you're creating a pipeline that is like a batch pipeline, but you want to optimize it for latency. And so you create a separate pipeline that's a streaming pipeline that like lands earlier and is the data is ready earlier because it's being processed in real time. And so how Lambda works is that you just have both. You double the code base. You have a batch pipeline and a streaming pipeline that both write the same data. And the main reason for that is the batch pipeline is there as kind of like a backup if the streaming pipeline fails. Or the streaming pipeline has problems or issues, or the correctness is a little bit weird, right? So the pain here is double code, right? That's the big pain of the Lambda architecture. Whereas you get a little bit niceness from like the data quality perspective and stuff like that, but the double code base is like one of the things that is a massive, massive pain for when you're creating this stuff. So that's essentially Lambda architecture. Like most companies, Facebook, Netflix, Airbnb, they like any of these like master data sets that they want to land as quickly as possible, but they want to be as correct as possible. They use Lambda architecture to solve that problem. Okay, so let's just talk about Kappa architecture real quick. Kappa architecture is where they say you don't need both. You can just use streaming. So like Flink, for example, you can actually flip Flink from streaming mode to batch mode. So you can actually have Flink just read in data and do the flip itself. So then you can have one code base and Flink can just handle the batch job as well. And that's good. It has some problems when like, for example, backfilling a lot of history is hard because like Flink is still mostly geared towards reading from Kafka. And like if you're reading in like many days from Kafka, like the backfill is just super painful because you have to read in everything like in a row, because that's how Kafka works, is all the data is in a line. And so that is one of the things that is very painful about Kappa architecture, is those kind of backfills. That's why Lambda architecture exists, right, is to kind of minimize that problem. One of the things that's nice though, and this is something that Netflix is working on, is Iceberg is actually changing that, right? So it makes it so Flink can dump data to Iceberg, and then Iceberg, you can have a nice partitioned table. And so then Flink, if you need a backfill with Flink, you can backfill days at a time, right? You don't have to backfill the whole line, because Kafka just has like one line of data, right? Whereas Iceberg can have partitioned data, just like Hive and all the other kind of data lake kind of architectures. So that's what's really cool about Iceberg is Iceberg allows you to do these appends. So you can append and create and add more data to your pipelines as you go. Whereas Hive, you couldn't do that. And that's like a very big win for Iceberg. And that's like probably my favorite thing about Iceberg is that append, because it allows the streaming world and the batch world to be mostly married. And like, at least from what I've been reading, like Netflix is starting to be more open-minded about moving from Lambda architecture to Kappa architecture, at least for a certain percentage of their jobs, because of how Iceberg is unlocking and minimizing some of the pain that comes with with Kappa architecture and like having to source all your data from Kafka. So that's Kappa architecture. So remember, Lambda architecture, Kappa architecture, they're both kind of here. Like for me, like the company, the poster child of Kappa architecture is Uber, because they have they're essentially a 100% real-time company, which makes sense, right? Because they have to monitor where all their cars are at all times, and it's like they can't be delayed. So they're like, Uber is a very streaming first company, and like it's very in their nature to be streaming first. And so definitely it's which architecture fits which company does depend on like their business model and what they're working on. I'm not saying one is better than the other. I just think that it should be good for you to be aware of both of these. And like this question shows up in data architecture interviews all the time. I've been asked this question in data architecture interviews at like every single company I've interviewed at since I became a staff engineer. So yeah, so definitely learn more about these two architectures because they are very important. So we're going to shift gears here, go back to, so that was just a little aside about architectures that I think is important because it talks a lot about streaming. We're going to shift gears here to be talking more specifically about Flink. So Flink has UDFs. UDFs are for like custom transformations, integrations. We used a UDF on Tuesday. And that UDF, what it did was it called an API, and then it enriched our data set, and we added some new columns. That's great. So Python UDFs are going to be not as performant as like Java or Scala UDFs. And the main reason for that is because they have to have a separate process, which is like really gnarly. So you have like the regular Flink process that's running and crunching data. And then when you hit that UDF call, it actually has to push it out of Java and push it into Python. Python executes it, and then it pushes it back into Java. And so it has to, I don't know if y'all have ever used like Apache Arrow, and it uses like, essentially it serializes things into Apache Arrow, moves it over into Python, calls a separate Python process, Python runs, it returns its result, moves it back into Arrow, and passes it back to Java. Whereas if you are using pure Java, then you don't have to do any of that, right? And then you don't have like that, because in that case you end up having two extra serialization steps that you, or two extra serialize and deserialize steps that you wouldn't normally have. And so that's where you want to be careful. This is also this guidance we're going to talk again about next week. This is generally speaking also good practice and guidance when talking about Apache Spark as well. It has the same issue, especially with Python UDFs specifically, because you have this like separate process. So let's talk a little bit more about windowing. So this is going to get really kind of complicated and messy. So there is essentially two types of windows in Flink. You have a count window, and then you have time-driven windows. Those are going to be the two different ways that you can define a window in Flink. And you can think of this as kind of like group by, or like a window function in SQL. It's kind of like that, but different. So we'll go over a little bit more. So When it's a data-driven window, how that works is like you open a window and then you say this window stays open until I see n number of events. And then we have these time-driven windows, tumbling, sliding, and session. And we're going to go over each one of those like in detail, and so that y'all will be more aware of like what's going on there. So first off, let's go with the count window. Count window is very straightforward. So essentially how count windows work is they open on the first event, and then they close when n number of events happen. Keeping in mind that you can key here, where like you can say like per user, so it's like a window per user, kind of like in the window functions in SQL you have partition by. In Flink you get key by, and that's going to be so you can have your first event per user. And one of the things that's another important part about these windows, especially these count windows, is that the number of events may never come, right? Say you're like, I want 50 events to come, and then someone does 3, and then they never do the other 47, and it's like, okay, that window doesn't stay open forever. So you also have to then you want to specify a timeout, like might be 10 minutes or an hour or some sort of like whatever timeout makes sense for your use case, and then that will close the window even if the number of events has not happened. So these count windows are very powerful for funnel analytics, because funnel analytics oftentimes have a fixed number of events. Like for example, like the notifications funnel at Facebook was generated, sent, delivered, opened, clicked, downstream action. So like, I don't know, 7, something like that. So then like this count can also be a distinct count. So if they like click twice or open twice or whatever, like that's fine, and they can do that, and that is not going to be an issue. So that's kind of the idea, is how you can use these to kind of measure funnels, because funnels usually have a fixed number of events. And then you also want to set a timeout of like, well, I don't want them to wait around forever. It's like they click on a notification. I'm not going to wait, many days to see if they actually end up following through. So like that's where the timeout is very useful when you're kind of specifying windows in Flink. Okay, so now let's talk about tumbling windows. Tumbling windows are really are very interesting. These ones are very like these tumbling windows are the closest comparison with data in batch. So a lot of times when you're in the batch world, you have like hourly data or daily data, and those have like a window, and that window is like from midnight UTC to midnight UTC the next day, right? And it's like 24 hours, or it's from like 1 p.m. to 2 p.m. and it's like fixed. It's like from point A to point B, and then everyone in that window is going to be in that time, right? And that will be the window that you're looking for. And so that is like, this one is nice because it has it's just very obviously the same as it's very obviously the same as like what you would expect from like batch. So tumbling windows and batch are going to be the most similar, and you can obviously chunk data this way. And a lot of times this is what people do, is they make these tumbling windows and then they dump it to hourly data, and then you have data that's already processed hourly, and then you use batch once it's at hourly, and then batch picks up everything else after that. That's a very common pattern at Facebook, at least. So that's kind of the idea here. This is the most simple type of window. We're going to cover this in the lab today as well, this kind of tumbling window. It's one of the first types of windows that I think is interesting in Flink. Let's go to the next one. So then you have sliding windows. So sliding windows usually have a fixed width, but they can be like overlapping, right? So imagine if you have a fixed width window of an hour, you could have one that's like from 1 to 2, but you could also have one from 1:30 to 2:30. And both of those windows are an hour, and they're both valid, right? And so, and you'll see here how like you get these kind of like sliding overlapping windows, and you get a lot of very interesting patterns this way. And you get obviously you get more duplicates this way as well, like because you see how like these records here are in window 1 and window 2, so you have to understand like how these sliding windows, like how to manage them downstream so that you're not like double counting or like what you're looking for. So a lot of times that's the whole point here though, is that like you're not trying to aggregate all of these windows together. You're trying to find the window that has the most data. And it's like if you pick one window, there's no duplicates, right? Because then you're fine. You just don't want to look at all of it in aggregate, because if you look at all of it in aggregate, you're going to have like twice as much data, because all like pretty much there's going to be 50% overlap in each window. So one of the things to think about here, right, is one of the things that this can do though is it can find your peak time. Because if you have like a window that's an hour long, but it's like shifted every 30 minutes, then you can know like, oh, maybe I actually, my peak usage is like 12:30 to 1:30, as opposed to like, if you looked at 12 to 1 and 1 to 2, those might be kind of flattened out, because it's like the second half of that first interval and the first half of that second interval are really high, but then the other halves are kind of low. So then you can like, there's like a spike that's like, that crosses the windows. And so that could be it could be very useful for finding like those types of peak uses, right? It's also good for like when you're crossing the midnight boundary. This is a very interesting question that we had at Facebook when we were talking about counting daily active users, because it's like if you have a user that starts their session at 11:58 at night, like 11:58 2 minutes before midnight, and then it goes to 2 minutes after midnight. So it's like a 4-minute session. And do they count as daily active on both days? Like, because it's one session, right? And it's like, it's only really one continuous use. And it's like, and it's not very long on either side. So it's like, is that actually daily active for both days? And that's like one of those edge cases around midnight that can happen. And this sliding window was useful because one of the things it did was it showed us like just how many people we were like essentially double counting when we picked that time. And then we also did this crazy analysis where we were like, okay, what if we used a different time zone? What if we didn't use UTC and we picked like a different time zone that was more centered around a different place's midnight? And we showed that like you can actually change the number of daily active users by like an upward of like 7 or 8%. By just like changing the 24-hour period that you pick, because that's because of this fact of people who have these like short sessions that are overlapping with UTC midnight. So that's one of the things that these sliding windows can be very powerful at like finding, is they can find those kind of situations for you. And so anyways, sliding windows are great. They're kind of niche. Like I found, at least in my experience with Flink, tumbling windows are going to be a lot more commonly used than sliding windows. Sliding windows have like a very like specific use case. Like it's not as much for like general purpose because of this weird overlap problem. That's like why it's like why are we doing this to ourselves? Right? It's more for like a very specific analytical use case as opposed to like building out master data. So anyways, that's sliding windows. Sliding windows are pretty cool. All right, then you have session windows. Session windows are, well, this is the fixed length one. Oh, wait, hold up, I messed up. I need to update this slide. This slide's off. So session-based windows are different. So how session-based windows work is they are based, like, they're user specific. They're not like a fixed window. So it's like you can imagine when you sign in and you have your first event, that's the start of the window. And then the window will last until there's a big enough gap. So there's like a gap definition that you need to specify. Usually maybe it's 5, 10, 20 minutes or something like that, where there's like a gap between when you have no data and like when you have data. And so that is going to be the big thing that you want to look at with sessions. This is sessionization is something that y'all are going to be working on in the homework, and it's one of the more powerful ones that I've noticed that will, because this is the one that can really help you determine like how users are behaving, because you can see like when they first start using the app and when they end using the app, and so you can get a very clear picture of like how users are using your app in real time, because you can get the beginning and end of their session. So that's essentially how sessions work, and that's configurable as well. Maybe it's 1 minute or however much of a gap you're expecting from your users when they are navigating the website. But that's kind of the idea. Okay, we're going to cover this one last topic that I think is important, and we're going to do a little bit of this in the lab. It's kind of hard to emulate this stuff in real life because of the volumes, and like I don't have like the right setup for this yet. But so essentially, you have two ways to deal with out of order or late arriving events. And the way it kind of works is like if it's a little bit late, then watermarking is going to be good. If it's late on the order of a couple seconds, usually watermark is going to be great. If it's late on the order of minutes, then allowed lateness is going to be great. This essentially is like if you have a really, it all depends on like how late you are. It's very similar to like when you have a Zoom call with someone, and like usually if you're like less than 5 minutes late, you just don't say anything and you go into the Zoom call and like you act as if you're on time. But if you're like more than 5 minutes late, like you usually want to text them like, yo, I'm a little bit late. And then so that they aren't just sitting around like, what the hell's going on? So it's similar, like Flink has the same sort of idea where like you would think of like the watermark here would be like, okay, anything, as long as they show up in the next 5 minutes, like we're going to count that as like in order. But then if it's over 5 minutes, then we're going to count that as late. And that's where you have this like allowed lateness, which is like another way to do things. But one of the things that's rough about the allowed lateness is that if you end up getting that really late data, it will actually reprocess, and it will either generate or merge data that might have already been flushed, because that data the window might have already closed. So it might end up reading what was in the window that closed, and then bringing in this new event and then closing it again, and you might get another window, like you might get a second record. Or you'll get an updated record, like, and that's like where this allowed lateness can be really funky, and like how like the actual behavior behind what it does, and like it usually does the merge, but sometimes it does it adds another record. So that's the whole thing. That's where like for me, at least when I've been working with Flink, I'm all about watermarking, and I usually just don't let like if the record is 5 minutes late, the way I look at it is that like it's similar to like my Zoom call stuff, where like most of the time if I have a one-on-one Zoom call with someone and they're more than 5 minutes late, I assume that they're not coming. And that's like why I have most of the time I have allowed lateness set to 0. So I'm like, whatever. If it's super late, I don't care. But if it's within the watermark, that's fine. That's my perspective on that. But obviously it depends on the use case, because some use cases like you need to capture 100% of the data even if it is really late. So that is obviously not just like, don't take that advice for every single streaming pipeline, but probably for most.
Congrats on getting to the end of Streaming Data Pipelines Day 2 lecture. If you're taking this class for credit, make sure to switch over to the next tab so that you can get credit for the lab. We're almost done with this one, guys.
So with Flink, we got you saw in like the job folder here, we had this start job, which we actually still want to work with because of the fact that it dumps to Kafka, right? Because we have this write to Kafka, and then this write here will allow us to have a job that will essentially, we can have another job that reads from this, right? And that will make it so that we can aggregate on other things too. Like we can maybe aggregate along like country as well. So we can kind of see, we can build some kind of tumbling windows around that kind of stuff. So the whole idea here is we will end up using that name, right? With this process events Kafka, that's going to be the name that we're going to be working with. But one of the things that we need to do though is we need to create another entry point, because I don't know if y'all remember like in the oh wait, no, wrong one. So you know how in here we have in the make file, we have make job, which is like this big old thing here. We need to have like another line here, and we're gonna call this, we'll just call this like window job, like window underscore job. And then change this to, we'll just call it aggregation job, because that's the name of the file, and I don't want to rename the file. So aggregation job. So I'm gonna send this in the chat, but obviously this needed to be like actually in the in the file. There we go. Put this in the chat here so y'all can put that in the make file just so we can have that kind of up and running. So obviously, first thing I want to do here is I want to say make up so we can get all of our, okay, so there we go. We have Flink is now running. We have all that up and going. And like, let's go look at this aggregation job real quick, because I think that that's something that is going to be important. Okay, so you saw how this name here needs to be different. This create processed events source. This needs to match. If we go back to start job, it's called process events Kafka. That's what we're going to actually call it. So I want to change this name here to process events Kafka in the aggregation job. So one of the things that this allows us to do is let's kind of go step by step through this aggregation job. And I think that will make sense as to like what is going on here. So we have a log aggregation. This is going to be our job. You see at the bottom here, we have the main looking great. So in this case, we again set up our execution environment. We say we're in streaming mode, and then we create our table environment. This is very like standard Flink stuff that you're going to see in like every single job. Then we go ahead and create our source table, which is going to be that process events Kafka topic, which is actually dumped to from that other job. So what we want to do is on this screen, we want to say make job. And I don't know what's going to happen if all of us are running these jobs, but we're just going to go with it. So we have this make job, which is going to have those, it's going to have those two jobs running. And what you want to do is you want to keep this going, because this is going to dump the geocoded data into Kafka, into that new Kafka queue. And then what you want to do is open a new tab, right? So, right, and hold 1 second. Why is it so funky? See, it's like it didn't update. Like it's like, okay, whatever. It's like sad and I don't got my coloring, but okay. So anyways, in here, right, we could say make aggregation job, and it's probably not going to work, but it might work. And then we'll have our third job running, right? Okay, so it's breaking, right? Let's see what it's saying here. A group window expects a time attribute for grouping in a stream environment. Ooh. So let's see what's going on there. So it's saying that like a time attribute is the problem here. Okay, so let's go look at our things here, right? So one of the things that happened here is you'll see we have our tumble over, and then we have event timestamp. And I think in our table, yeah, see, we have event timestamp here, but it's a varchar, right? And that's like a problem, because that's not what we want. So what we need to do is we need to add another column here, which we can do. It's pretty easy. Like it's actually in the other job. We need to do that. So what we want to do is, where is it? There, I have a perfect example here. Yeah, this one. So we want to get this pattern here, because I think we have because we end up writing it out, and oh yeah, no, we want this pattern. This is going to be the pattern that we use. So, but that's fine. We can copy this one and just get rid of the Z and the T. So we go back to the aggregation job. Okay, we have this pattern here, but we actually don't have the T and we don't have the Z, because this is the pattern that we actually write out. I think that matches this format, right? Oh no, there's just no .sss though. We have just the lower. We just have the little s's, not the uppercase s's. Okay, so I think those. Well, what I'm gonna do? I'm just gonna copy this. It's like make it be exactly the same. Okay, now we know for sure it's exactly the same. And so what we want to do here is we want to make a new field here. We're gonna call this maybe like window timestamp, and then we want to do it the same way they do it in this other job. So there's like 2 timestamp, right? 2 timestamp. So this one, we want to grab this. We'll say as like that. So window timestamp as 2 timestamp, and then this is not event time. This is event timestamp, because like it's the same as this one. And then that will use the pattern that we shifted it to when we wrote it out in the other job that is currently running. So that looks right. That looks good to me. So one of the things here is that should fix our problem for the rest of this code. So one of the big differences here, though, is now you'll see down here where we're defining the window. See, okay, so we have our source, which is great. And then we have our aggregated table and our aggregated sync, which are working fine. But then what we have here, you see this tumble. We have this tumble over. So this is going to be we're going to have a window that is opened every 5 minutes. And this is now this is where we want to update this to window timestamp instead of event timestamp. And that should give us what we're looking for as kind of the idea of so this is going to give us our window, and this is where you see we actually get group by here, and so this is where we're going to get a little bit of a key, right? So we're going to have windows that are based on both host and based on time. So we'll have 5-minute chunks. So what I want to do here is I want to say make up, because we need to essentially start them up. And oh wait, that did not. Okay, I think we actually have to kill the other job real quick, because we need to do make down, because we need to get the new updates into the aggregation job, right? So make down, make up, so we can get the actual job running here. So there we go. Now that's running, and I want to go back to the other tab here and say make job, because that should give us the actual data here. There's probably more steps that we're going to be missing here to get this aggregation actually up and running. But so now that's working. That's the other job. But then we can say make aggregation job over here. And so this is hopefully going to work now. Okay. A group by window in the stream environment. Isn't it giving? It's the same error. Why is it mad now? Is there another? It's because it's here. You got to do it in both, because it's the same problem here, right? Because we have another job here that has the same problem, so we need to change this to window timestamp. And obviously, if Flink is not syntactically correct, it's gonna make that mistake, right? And we'll go over both of these windows here in just 1 second. I just want to get this job up and running, so we've got to do the same make down, make up, madness, right, to get the new code there. So then we can do make job. See, it just kills it if you do make down. Cool, great. And then now here we can say make aggregation job. Oh, is it gonna work? It might work. How is it still the same bug? Because now this is now this is right. Because now we have our window timestamp, and that seems right. And we have everything here that seems to be what we're looking for. Because then we have event hour, window timestamp, and then we shifted it up here, right? And we have our 2 timestamp pattern here. That seems right to me, though, because then we have our group, which is our table name, which we are doing right here. So, okay, why is it upset? I want to look back at this. So we say validation error. A group window expects a time attribute for grouping in a stream environment. Does it have the actual line? Oh, because this is all in Java, right? And it's no. We can't do it. Okay, so that means it's actually failed. It's getting here, and then it's not working the way you would expect, though. So let's kind of go through this a little bit and see what it could possibly be here, because we have the window timestamp here. And what about this aggregated table? Is there something in here that is okay? That's timestamp. That's fine, and that's event hour, which should be fine. And then interesting. That's so weird, because I definitely had this working before. So we have the window timestamp, which is going to be right. I mean, unless it's not processing it right, if it's not this actual window timestamp here, if this is not doing the right thing for some reason, if this is parsing it wrong, then that could be what's going on, and that it's not actually processing that the right way. But that seems right to me, because that's how we are dumping it out over here, right? Because I think that's the problem here, is that the date format here is not giving us the timestamp that we're expecting. it to give us, and that's like why it's like yelling at us right now. So, anyways, okay, there is one of the things I want to try here is if we change this to latest, just change this to latest real quick and try it with that, because that will like essentially have it show up as like we'll only get the latest data, and maybe there's like weird data in Kafka that isn't parsing, and that's the reason. And so now we'll only get the latest data. That might see if this barfs as well. I'll be surprised. A group window expects a time attribute for grouping in a stream environment, and then this has got to be that line. It's got to be down here. That's got to be like literally right here. That's the only line that even makes sense. We have I want to go over the code, and I know that there's just like a small like timestamp like casting problem here that I will figure out, but like here's kind of the idea of how tumbling works, right? So you define a window, which in this case we're going to do every 5 minutes, but this can be every 5 minutes based on processing time or based on the event time, right? And in this case, we're trying to do the event time, which usually is what you want to process on. You don't want to process on processing time. And then what we're going to do is we're going to group those windows together. In this case, we're going to group on the window and the host. In this case, we have our host here. And then from there, we have our event hour, host, num hits, all that stuff. And then this is going to essentially do an aggregation every 5 minutes, or hopefully. That would be ideally, that's what's going to happen here. So what I want to try, I want to just try one thing real quick. I want to try using the other like the other pattern here, because I still wholeheartedly believe like what is going on here is this pattern here is just not like maybe we want to try two more tries here on using this pattern, and then also the pattern with the seconds. So we'll try the second ones first, and then we'll try the one with the Z and everything in it after that. And then if both of those don't work, then I have failed y'all, and like we won't be able to, like there's going to be like some other crazy thing going on here. But this should with the seconds, is it gonna give it to us with the millis? Okay, with the millis it still has the same problem, but like what about if we change it to the exact same one that we had, the exact same pattern that we have from the other job. Okay, so actually no, because it's failing without even reading in data. So it's saying it's not like this timestamp is not right. It's like, oh, it's saying expects a time attribute for a job, right? And so I wonder if it's like it's not like time. This is like a time, like maybe there's a difference between time and timestamp. Yeah, Kyle, do you have any thoughts on this? Curious. Like, ooh, dude. If that's what it is, like, oh man, that actually freaking probably is what it is, dude. Let's just throw in the watermark real quick. We'll call this we're gonna call this window timestamp, and then as we're gonna say window timestamp. Dude, that's totally what it is. That's totally what it is. And then this is gonna like this is gonna just be that, right? It's gonna be that regular one that matches the other pattern. You're totally right, 100%, dude. That's totally what it is. It's like totally forgot the watermark, dude. If this just works now, like it probably will just work, and then I'll feel better. I don't. It's not failing. It's definitely getting first. Yeah, boy, let's go. Thank you, Kyle. You saved my life right there. This was almost a demo fail. Okay, so let's go look at like what is going on in Flink here, because we're gonna have a lot more jobs running, right? So we also, we need to run the other job, right? So we need to do like make job over here. This might actually not let us do all four. So I will, I'm going to send y'all that watermark definition here in just 1 second too. I just want to see if, there we go. So now I think the problem here is that we don't have slots for 4. Yeah, we only have slots for 3, but okay. But so one of the things I want to walk through here real quick in like these window jobs is that they are more complicated. So you'll see in this case, we actually end up having there's like two records here, right? You have or there's like two steps, right? Because you have the first step of like reading in the data, and then you have the group window aggregate step, which ends up. So this is where watermarks are useful. This is where because watermarks, like if you are getting data and you're just reading and writing data as like rows and you're not doing any grouping, then the ordering doesn't matter that much, right? But now you'll see we have a watermark, and Kyle's totally right in that like we needed to have that watermark, right? That was exactly why we couldn't window, because you can't window without a watermark in Flink. So what we need to do is we need to go and create that table real quick. So we can say create table, processed, events, aggregated. And in this case, this table has 3 columns, I think. There's there's 2 tables here. Yeah, there's processed events aggregated and processed events aggregated source. So these are 2 separate tables, but like you can essentially just create them from the DDLs in Flink. I will pass this to y'all as well, so that y'all can have this. But so this is going to be our first one where we have our processed events aggregated. And then we also have one for source, because we wanted to also look at who is winning based on like not just like who's winning from Twitter, who's winning from which place, right? So we want to say create table. This is processed events aggregated source. This has these 3 columns in it. I want to run this guy. So now these tables should be already processing though. Like once you make them, like it should just immediately be pumping out data. Right, there we go. So now you'll see we have essentially data coming in every. We have data for like every 5 minutes, right? Essentially for all of these. You'll see that a lot of this data is for like exactly and tech creator, which makes sense, but we should be able to say where host equals, we can say zachwilson.techcreator.io, because this should give us other data. There we go. Because now you'll see this 1855, this is going to be the one that really is the one voting. So then you'll see we have three hits there. So really we want to put an in here. So we want to say Zach Wilson, we want to say lulu.techcreator.io, and we want Dutch engineer. So Dutch engineer is Sarah. So we have dutchengineer.techcreator.io. And so then we have our 3 here, and then we should be able to run this. And there should be more data than that. There we go. So you'll see here we have our data coming in. And oh, this is like for the 9th though. So you'll see in Docker Compose here, in this Docker Compose, at the very bottom, you'll see this task manager, number of task slots. I'm going to bump this up to 5. And then I'm going to just, we're going to do make down, and then we'll essentially make up, and then make it so that we don't have any jobs that are like failing because they don't have enough task slots. We can say make aggregation job. But like that's a great thing, and we're about to find out if we need to increase parallelism or not. And so this should work. Okay, so if we go back to running here, we should have 4. Yeah, we're good. We're good, because like you should see some like purple here, but you don't. You see how there's no purple? Like it's all running now. It's all looking pretty good. And so now, I mean, we should be seeing way more than this though. Like this is trying to like say that like freaking nobody has clicked on my links. Like I don't believe that. Because like that doesn't make any sense to me at all. Like there's because unless the data it's still like chugging through all the data, which okay, so if we go to the processed events aggregated source, if we go into here, this should be like pumping data, right? Okay, it is. So one of the things you'll see here is like it actually does give out like data sets here, right? So you see it says like, okay, we've sent 500 records and we've received 200 records. Oh, I bet it's because of the 5-minute marks. Like these 5-minute marks is probably the thing, because we have that window and it's like needing to open and close these windows. But a lot of those windows should be done. Like a lot of those windows it still seems very strange to me that there's no. What if we look at the source table? Processed aggregated events source. Okay, this is looking again though. Again, we do. Okay, see there's someone. There is someone who's coming from Twitter. Like that's what T.co is doing right there. Like, but this is still like seems wrong though. This still seems like this is off by like a day. Like the time is not like because it's not the 9th, right? It's actually the 10th. So that seems really weird. Like that might be like a latest thing, but like I swear we are processing on each thing here. We're only processing latest. If we go to the aggregation job I put in here, right? There's just we use latest offset, and then in the start job we're doing earliest offset in the start job. So that might mean that it's still pumping out new data into Kafka. There should be way more records here than 8. There should be like because it's like this is like for every 5 minutes. Like there should be like way more than just like that's so strange to me that like because it's weird that it's like processing data, but like it only has like this many records, right? And it's like and this must just be like spare traffic that like it's not actually okay. What about the other job though? Because this other job should be what this process events Kafka. This job, there it is. That's why. This guy is struggling. That's why. This guy is definitely struggling. This guy is not writing data right now. That's what's going on. I think you're totally right, Kyle. That like this guy is like he's like he has like he's kind of backed up, right? He's kind of backed up. I wish I could like so this is like I think this is a great example of where like so what we should probably do here and this is an easy fix I feel like which will make it so we can at least get some new data from people who are coming in is so I'm gonna stop the start job and then what I'm gonna do is let's go back into that job and change this earliest offset to latest offset so that like we aren't like processing like everything, right? We just process the new data and that should make a pretty big difference. Oh wait, I gotta do the whole thing. I wish that like it would just put it up there and I don't have to like Docker all of this all the time. But this should make it so that we have more of a like actual kind of data set that can pull in more like it will only pull in like new data as it comes in. And then we have to like have that like kind of those 5-minute sort of interval things, but at least then we'll have data that's like it's not just like struggling. But you're totally right. That's exactly what was going on. Is that like it was not like it was totally not like it was struggling to read all of the data because of the fact that I don't think it's because I'm so popular. I think a part of it is because like a lot of y'all have been running the jobs, right? And so that Kafka queue actually has a lot of duplicate data in it. I want to see real quick. That's actually like that's a good little thing that we can add to this lab because now okay, all my jobs are up and running now, right? We got okay, they're all up and running, and so now this should have more up-to-date data, right? Or it's just gonna not have. Oh no, it's because it hasn't been 5 minutes. It hasn't been 5 minutes. We have to wait till 7:40, and then we will see because that's when that window the tumbling window will close. But I'm like in the meantime, we can go see how like messed up Kafka is, like and see how much data y'all like dumped into Kafka because I bet it's gnarly. Okay, so here we are. Here's Kafka. Oh, look at that. What are we? Whoa. This is not what I'm looking at. I want to look at process events Kafka. Okay, it's saying that there's just like 25 megs in there. Not like obviously something happened here with this IO sex, right? And I think it might be because I have just like a really like tiny Kafka cluster, and that's what's going on here, and that's why it can't like handle it, right? Because bootcamp events, I'm guessing, is probably going to be fine. Oh yeah, but you can see that there is a step up here from like when I made that post. So there is more data in the queue for sure. For sure. I'm just trying to get it like to have so we have like Flink into Flink. That's like the idea. That's what I wanted to like really show in this class. There we go. Okay. We're good, fam. It's there. We hit the 5-minute mark. So now we have the 7:35 window closed. And you'll see Sarah is beating me by 1, and then Lulu has 16 hits. And so that's kind of the idea. And you'll see if we put in like source here, then the 5-minute window here closed as well. And then you can kind of get the breakdown, and you'll see like Twitter hates me. I literally have no votes from Twitter. None. Not even one. All my votes came from LinkedIn. That's so sad. Lulu's got some love, some Twitter love, and then someone went directly there too. You see, there's like a null. So Lulu is like mostly LinkedIn, 12 from LinkedIn, 3 from Twitter, and then 1 direct. So in this kind of competition that we're doing, right? So this is working now. This is working, and I'm glad it's working. And we kind of discovered like what's going on and why this is happening. That's where this like latest offset versus earliest offset does make a pretty big difference, especially like when you're processing things, because like you might end up like trying to read in all the data sequentially, and like if you're doing windowing on that, that just becomes like even more gnarly, right? So that's essentially what's going to happen here, and we're going to build out some more like stuff here. Well, one of the things I wanted to go back over here with oh wait, not that one, with in the aggregation job. So let's go back into the code now that we actually see it working, and I'll show you essentially like what is actually happening here, right? So we are reading in our source table, we're doing a 5-minute window, we're grouping on the window and the host, and then we're essentially, this is giving us our time, and then we have the host and then the number of hits. That's what is in here when we get rid of source here. If we look at this table, you'll see that's exactly what's going on here. We have the time and the number of hits. And obviously this does have that little bit of latency, but you'll see like in 2 minutes, we're gonna get more data, and we'll have like more data for every 5-minute interval. And that's like what's really powerful about this, is that it just like automatically shows up. It's pretty cool. And then the only difference between that one and this next one is we also group on referrer, which is going to be like, did they come from Twitter? Did they come from LinkedIn? Like, where are they coming from? And so it does this aggregation kind of in real time, which is pretty cool. Like, do we need to do this in real time? That's a great question, because sometimes aggregations are things that we don't maybe necessarily need to do in real time. So this is kind of how tumble windows work, and like we're going to be able to see as these windows close, like how they kind of process over time, which I think will be pretty cool to see. One of the other things that we could do here that like would probably, you saw how that choked, right? That the last job kind of choked. Because of the fact that it, one of the things that we can do, and I want to try this actually. I think this is something that I think would be pretty cool to see, just to see like if it actually does the right thing. I think that this will be a nice little experiment. So what I want y'all to try out is like maybe change the offset back to earliest offset for the aggregation job. So what I'm going to do is I'm going to kill the aggregation job real quick. And then what I want to do is you'll see how we have this amp.set parallelism. So let's set that to 3 so that like maybe we can have, because that's how many, if you saw in this process events Kafka, you'll see that we actually have 3 partitions of data. So we know like that the data is split up in 3 buckets already, and so that will be something that will help us get more like parallelism, and we should be able to crunch this data a lot faster if we have 3 tasks versus 1. So then what I want to do is I want to say make down, and then make up, and then here I want to say make job. And here I want to say make aggregation job. And then I just also want to show y'all what that looks like differently in the Flink UI, because this is essentially how you set the parallelism so that Flink knows how many tasks to kind of spin up. I'm wondering if we might need to have more task slots, but I don't think so, because I think in this case the task and the parallelism are separate. I think it's like workers, but that I want to be more sure about. Okay, so we did. Okay, so you see here how this one is, we're running out of, see how we get, these are scheduled tasks, right? So you'll see in here how we now have parallelism of 3, but this is 3 on each on each task here. So the number of task slots here, we probably need to bump this up quite a bit because there's actually going to be, because here, you see how this changed to 6? That's because there's there's the default parallelism is there's 3 tasks per stage, and so we have 6 and 6 here, so that's 12, that's 14. I want to change this to 15 real quick. I'm going to change the this guy to 15 just so we have like enough spots. And then let's try make down one more time just to kind of show y'all how, like, because you really do want to learn how to work with parallelism and all this kind of stuff, because these are the real problems that happen in streaming, right? This happens all the time. So like, and this is the kind of things that will, like, just kind of playing around with this stuff will, hopefully this is going to give us what we're looking for. So boom, 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 boom. And then this should be able to just crunch the data way faster. Like we can have like this like beast mode kind of crunching of the data. Okay, there we go. Now we're getting some more jobs in here. Okay, initializing. There we go. Now see, now I got the 6 and 6s running, and so that's great. That's gonna make it so that these things are running way faster, right? We should be able to see like way more data coming in through here, and it should just kind of crunch all through it, and we should see a lot more data showing up in Postgres as well. So okay, so there, okay, so you see it did process the next one down here. You see this is the 740 slot, and I did a little bit better there. I was able to swing and get 25 in that case. So this seems to be working actually. I think like I'm guessing there's actually like a lot of data here. Okay, there we go. Now we were able to crank it up and get the parallelism up to like what you would expect. And you see now it's just like, it's making quick work of that data. Like it's just like, it was able, instead of feeling clogged, right? It's just murdering it now because it's splitting it all up and it's reading each partition at once. So we're getting at least a 3x speed up here. And so that's what this parallelism is going to do. Seems like this is working pretty well now. And so you definitely want to, there's like this kind of trade-off, right, between like parallelism and this stuff. Like one of the things that's nice about Flink versus Spark in this way is that the parallelism numbers are usually lower, right? Because like you see how I moved it from 1 to 3. Like in Spark, you're always like thinking like, oh, should this be 200 or 100 or how many tasks or how should this split up, right? And because, you know, in Spark, the default is 200, but in Flink, the default is 1. Because and that's like one of the fundamental differences between batch and streaming, though, right? Is because in streaming it's like, okay, we're going to process the data as it comes in, and that's going to give us what we're looking for. And now this is going to essentially just work, and it will make super quick work of it. But obviously, one of the things here that can be kind of tricky is now like this job is going to be running all the time, and there's going to be times when there's not a spike in the data. And we don't need 6. We really don't need 6 tasks to process the data. We need 1 or 2, and that's where it's a trade-off, right? Where I bumped it up to 6 because I wanted to show y'all in this lab, and I was like impatient, right? And I wanted to show y'all like how this actually is gonna work. So because you'll see in here, you can see how the votes are coming in, and we can actually even see. Let's see the source. We can look at source too. Okay, so why is it like not all ordered? Okay, there we go. Did I get any Twitter love? I hope I got some Twitter love, right? Oh, like, okay, good. 3 people. One of the things that I think is important here is that there is so many just like jobs that you can run, right? And that like I think one of the other important questions here is like, should these jobs be ran? Should this aggregation be ran in Flink, or should it be ran in Spark, or like should it be ran in batch? Should it be ran in streaming? Like, how do you know? Like, because they both add latency, right? This adds 5 seconds of latency, or this adds 5 minutes of latency, right? And so it's not like you're just like you get this for free, right? In terms of latency. So one of the things to think about there is, okay, like what kind of aggregation are you doing over what time frame? So one of the reasons why this aggregation is really nice to do in Flink is because it's a 5-minute aggregation. And since it's a 5-minute aggregation, like doing that, like imagine running a Spark job that ran a group by every 5 minutes. Like that job's a joke because it's like the time it takes to start up freaking Spark to then run the group by is going to take more than 5 minutes, or it's going to take like 3 minutes just to start up, and then it's going to run its query, and then it's going to essentially be running the whole time anyway, except like you're going to have all this startup and teardown cost, where Flink is actually going to run more efficiently in those cases. And so like there is a line where I think that it flips, and I think that that's generally at about an hour. So if you have a group by that's like an hour or longer, then that's when batch kind of wins and kind of takes over. Like if you're trying to group and dedupe over like longer periods than an hour, then you probably want to do this. You don't want to do a tumble window that's an hour. You do a tumble window that is, I don't know, 30 minutes or something like that, and then you do another aggregation in Spark for the hour or the 5 hour or whatever, however big of an aggregation window you want to do. Like generally, that's kind of like what I've noticed when I've been working with streaming. But that's kind of, there's a line there between like hourly and like sub-hourly where that's where it kind of transitions from like you should do the aggregation in streaming to you should do the aggregation in batch. Obviously, this only matters at like that rule of thumb really only matters when you're working at very large scale. Like you can like Flink is totally possible. Like at smaller scales, you can have Flink do a daily aggregation and just hold on to all the data like this and kind of aggregate it down, because this is not that much data. Like it really isn't. So like, and since this is a 5-minute interval, it actually writes it out and it doesn't hold it on to memory anymore, right? Once the window closes, it writes it out and it persists to disk at that point. So you don't have to like have tons and tons of RAM. That's why batch is better for bigger windows though, because Flink just needs a weird amount of RAM in order to like hold on to so many windows for so many windows that have so many like data points for such a long time. Whereas like Spark is going to be able to handle that much better. So yeah, I'd say that that's kind of the perspective of like how to do these aggregations.
Congrats on making it to the end of the streaming data pipelines course. It's one of the most complex things that you can do in data engineering, so I'm proud of you.